Hello my dear student, how are you? I hope all of you are well. So today we are going to start GATE 2023 one shot series, and today's lecture number 1, that is theory of metal cutting and tool life. So in this session we are going to cover theory of metal cutting and tool life in one shot. So let's start our session. My dear student, first of all you have to understand what do you mean by machining, right? What do you mean by machining? So machining is what? Basically machining is, let me here explain the term of machining. Machining is what? It is an essential process, right? It is a essential process of what? Of finishing. It is an essential process of finishing, by which jobs are produced to the desired dimension and the desired surface finish. Now the question is, how can we obtain the finishing process? The finishing process is obtained by gradually removing the excess amount of material, from the preformed. The meaning of preformed is initial. Preformed blank, that is the initial workpiece. From the initial workpiece we are removing the excess material in the form of what? In the form of chip. So overall we can say that machining is a removal process. My dear student, I have one question. We are removing the excess material, right? We are removing the excess material. So let me draw here. Let me draw the figure. Suppose that this is my workpiece. Right? This is my workpiece. Okay. Yes. Suppose that this is the given workpiece, and I have to remove the excess material. Okay. That much excess material I have to remove. This is the excess material. Now the question is, the excess material is going to remove from the workpiece with the help of what? With the help of tool. So this is the tool. Okay, so this is what? This is the tool. See, this is the tool. So my dear, this is what? This is the tool, right? This is the tool. This is the tool. So that much excess material we are going to remove. How much? That much. See, that much excess material we are going to remove. Now that excess material is going to remove by the tool in a single shot or in a single stroke. The another process in which we are going to remove the excess material, right, by layer by layer, right, by layer by layer. We are going to remove the excess material by layer by layer, right, layer by layer. See, layer by layer. See here. Now here I am going to remove that excess material, okay, with the help of tool. I am going to remove that excess material with the help of tool, layer by layer. First I am going to remove that layer, then that layer, then that, and finally this. So the question is, both the thing is, in both the case we are doing machining. In process 1 and in process 2, in both the case we are doing machining operation. Are we getting a desired dimension and good surface finish in case 1? No. We are getting the desired dimension and good surface finish in case 2. Why? Because we are removing the material gradually. When we are removing the excess material gradually in the form of chip, then you get the desired dimension and surface finish. So this is the case of what? This is the case of finishing, right? This is the case of finishing, right? Here also we are doing the machining, but this is a case of rough machining. This is a case of rough machining. This is a case of what? Rough machining, my dear. This is a case of rough machining, and this is a finishing. It is a machining, but it is a case of what? Finishing. And we want a finished product from the machining, right? By default, from machining, we want a finished product. So I hope you understand the meaning of machining. By default, the meaning of machining is what? Finishing. Okay, finishing. If finishing is not given, then we will consider as a rough machining, right? Now let's move to the further. Suppose that we are removing that excess material in the form of chip. As you can see in the figure, we are going to remove, okay, we are going to remove that excess material, right? We are going to remove, okay, suppose that this is a T0. I hope you know the value, you know the meaning of T0. T0 is the uncut chip thickness. T0 is uncut chip, okay, uncut chip thickness. T0 is what? That is uncut chip thickness. Now the TC, that is what? That is a chip. TC is the thickness of what? Chip. So here TC is thickness of chip. Thickness of chip. TC is what? TC is a thickness of chip. My dear student, when the tool is moving toward the workpiece, when the tool is moving toward the workpiece, this is a tool which is moving toward the workpiece with a cutting velocity V. V is what here? V is basically here, let me write down, V is cutting velocity. Okay, cutting velocity, right? So tool is moving toward the workpiece with a cutting velocity V. Now when the tool is going to enter into the workpiece, what happened in the primary deformation zone? In the primary deformation zone, the crystal structure is going to break, right? The crystal structure, the crystal is going to break. CRY, crystal structure, crystal structure, right? Crystal structure is going to what? Is going to break, right? Is going to break. So lot of bonds are going to break. For that it require, or you can say in that zone, 70 to 80% of total power. 70 to 80% of total, okay, total power is required, okay, is required to break the crystal structure. Now this crystal structure is going to break because in this crystal structure a force, that is what? Shear force, right? That is what? A shear force. A shear force is acting in that zone, and because of that, whatever be the crystal structure, whatever be the crystal structure is going to what? Is going to break, right? For that it requires 70 to 80% of the total power. So initial deformation will be happen in that zone. That's why we call a primary shear zone, or sometime we call as primary deformation zone. We also call as primary deformation zone, right? Deformation zone we also call as primary deformation zone, because initial deformation will take place in that zone. So AB is a shear plane which makes an angle, okay, which makes an angle phi here. Phi is a shear angle. A shear angle which is made by shear plane from the horizontal axis. So phi is a shear angle. Now when the chip is moving in the upward direction. After deformation, what happened? After deformation, crystal structure is going to break and it is going to convert in the form of what? Chip. Now the chip is moving along the rake face of the tool. My dear student, this is what? This is the rake face, right? This is what? This is the rake face, okay, or rake surface. Rake face or rake surface. What is a rake face? A surface of a tool along which chip is moving, okay, and that surface, right, and that surface of the tool is known as flank, okay, a flank. Basically, the flank surface is toward the finished surface of the workpiece, because this is the cutted portion of the workpiece, or you can say machined surface, right, machined surface. It is a machined surface, okay, or you can say a finished surface, right, finished surface. It is a finished surface. So flank is toward the finished surface. Flank is the surface of the tool which is toward the finished surface, and rake face is the face of the tool on which chip is moving, right. Now the question is here, the chip is moving in the upward direction along the rake face. The chip is moving along the rake face. There will be a rubbing action between the chip and face of the tool, between the chip and rake face of the tool, right. And because of rubbing, my dear, what happened? Because of rubbing, lot of heat is going to be generated. Because of rubbing, lot of heat is going to be generated here. I am talking about here in the secondary deformation zone. This is what? This is a secondary deformation zone, okay. Secondary deformation zone. Secondary deformation zone. This is secondary deformation zone. In secondary deformation zone, there will be a friction in between the chip and tool, that is a rake face. So drag, friction comes in between the chip and, okay, in between the chip and rake face of the tool. Now to overcome the friction, or you can say drag, it required 25% to 30% 30% of total power. Of what? Of total power, my dear. So it required 25% to 30% of the total power to overcome the friction. So again, the heat is going to be generated in the secondary deformation zone. But here, the heat is going to be produced after the primary deformation zone. That's why we call a secondary deformation zone. So I hope lot of thing is clear. Let me write down what is phi here. Phi is a shear angle. Phi is a shear. Okay, phi is a shear angle which is made by a shear plane, which is made by AB. That is a shear plane. That is what? That is a shear plane, right? Shear plane. So shear plane makes an angle phi from the horizontal, or you can say from the cutting speed V. Along the shear plane, deformation will take place. Okay, deformation is take place. Deformation, okay, is take place. Where? In the shear plane, right? Because shear force is acting. So I hope lot of thing is clear, okay, from this figure. And let me give you, phi is a shear angle. Let me explain one more angle. This line is called, my dear, this line is called normal line. Right? Normal line. Now, a angle which is okay, angle, this angle, angle which is made by the rake face, angle which is made by a rake face from the normal line is called a rake angle. So alpha, my dear, here alpha is what? Alpha is a rake angle, right? Alpha is what? The rake angle. So we are going to discuss about alpha, we are going to discuss about the shear angle and the shear plane in the upcoming slide. So don't worry, right? So don't worry. Now let's move to the next page of this slide. As I told you now, as I told you, this is the primary deformation zone. Here the crystal structure are going to break, right? Here the crystal structure, here the crystal structure, the bond, okay, the crystal structure. This is a crystal structure. This is a crystal structure which is going to be break, which is going to be break with the help of, okay, with the help of what? With the help of that shear force, with the help of that shear force. This is a shear force, right? This is the shear force, Fs. Fs is what? Fs is a shear force. Fs is shear, right, force, which is acting along the shear plane. And here A and B is a shear plane, and that shear plane is make an angle phi from the horizontal or the cutting axis. Now, my dear, please see here one more zone. That is what? That is the secondary deformation zone. See here, that is the secondary deformation zone, right? Are you able to see? This is a secondary deformation zone. And what do you mean by the secondary deformation zone? A zone where rubbing, where friction will be occur between the chip. Okay, this is a chip which is flowing in upward direction. Okay, a friction will be occur between the chip and the face of the tool. So this is what? This is the secondary deformation zone. Here the tertiary deformation zone is very small. So generally we are not going to talk about the tertiary deformation zone. Now see, I'm going to show you the shear plane in 3D. Suppose that it is a two-dimensional figure, right? It is a two-dimensional figure. Now you can see here AB is a shear plane, right? You can see here AB is what? AB is the shear plane. And maybe you will ask from me, sir, show me the shear plane, right? Show me the shear plane, because AB here in this figure, AB will be look like as a line, and I want AB is going to be look like a line, and I want to see a proper shear plane. Okay, for that I'm going to show you a three-dimensional figure. Suppose that you are going to remove the chip. Okay, in that case I'm going to show you the width of the workpiece. Okay, see here, this is what, my dear? This is what? Okay, this is what? This is a T0, right? This is a T0, that is the uncut chip thickness. Okay, so this is a two-dimensional figure in 3D. That is the width of the workpiece. Now AB, that is what? A shear plane, right? AB is what? A shear plane along which a shear force is going to be act, right? Along which a shear force is going to be act. So this is what? This is the shear force which is going to be act, to deform the workpiece, right? To break down the crystal. So along this plane, deformation is going to be take place. Now the inclination of the plane from the horizontal axis or from the cutting velocity is known as phi. That is a shear angle, right? T0 as usual, that is a uncut chip thickness, right? Now here W is what? W is, my dear, here W is, that is the width of the workpiece. W is what? It is width of the workpiece, okay, of the workpiece. Now whatever be the width of the workpiece, it will be the width of the what? Width of the chip. So W is also the width of the chip, and right. Now suppose that if this is the shear plane, okay, AS is what? Here AS is what? Here AS is the shear plane, okay, that is a shear plane area, right? Shear plane area, which is denoted by AS, which is denoted by AS. Now I want to know the value of shear plane area. Okay, so what is the value of shear plane area? That is the length of the shear plane, that is AB, into the width of the shear plane, right? The width of the shear plane. Now, what is the length of the shear plane? As you can see in triangle ABC, here BC is perpendicular, right, to the AC, and BC is also equal to what? The T0, and phi is a shear angle. So in triangle, okay, so in triangle ABC, in triangle ABC, see here, the sine phi is equal to perpendicular, that is what? T0 by what? By AB. By what? AB. So my dear, AB will be what? AB will be T0 by sine phi, right? AB will be T0 by sine phi. So AB, that is the length of the shear plane, and W, that is the width of the shear plane, right? That is the width of the shear plane. So W into T0 by sine phi, that is what? The value of AB. Now you get the value of the shear plane, okay, shear plane area. Suppose that tau naught, that is what? Yield, that is yield shear strength, that is yield shear strength, okay, yield shear strength of workpiece is given, okay, yield shear strength of the workpiece is given. So can you find out the required amount of shear force? Yes, we can find out the required amount of what? The shear force. Required amount of shear force will be what? That will be tau naught into what? AS. This is the required amount of shear force, okay, to break the crystal structure. And why the shear force is going to be produced? Because of the cutting force of the tool. Because of the cutting force of the tool. So I hope this point are crystal clear to you. So let's move to the next slide. As you have seen here, that there will be an inclination of the rake face from the normal line, which is called what? Which is called a rake angle. Now let's talk about the rake angle. My dear, the rake angle of the tool can be positive, negative and 0. Here the rake angle is what? In this figure, according to this figure, here rake angle is what? Here the rake angle is positive. But the rake angle could be 0 or negative. So let me show you the negative or 0, okay, rake angle. Why here the rake angle is positive? Okay, let me explain you this thing. Suppose that the tool is coming from this side, having a cutting velocity v, right? Now see the inclination of the rake face from the normal line. This is what? This is a normal line, okay, is what? This is the alpha. That alpha is lie in the side of the cutting velocity. That's why we called as a positive rake angle, right? So this is a positive rake angle. Now my dear student, see here, again the tool is coming from this side to cut the workpiece with a cutting velocity of what? V. Now here the chip is moving, here the chip is moving in the upward direction, right? The chip is moving in the upward direction. Please see, the chip is moving along the, or you can say the chip is moving along the normal line. This is a normal line, right? This is what? This is the normal line. This one is what? Normal line. And sometime we called as a reference line also. So this is a reference line also, right? Sometime we called as a reference line. So the inclination here, see, this is a rake face, the inclination of the rake face, and rake face is what? Rake face is that surface from which the chip is moving. Here the rake face is this, and the inclination of the rake face from the normal line or the reference line is what? 0. So this is a 0 rake angle, 0 alpha, right? 0 rake angle, right? Again the tool is coming to cut the workpiece from this side, right? With a cutting velocity of what? With a cutting velocity of v. Now see here the inclination, right? My dear, this is a normal line and a reference line. So from where the tool is coming, that side I will take a positive and other side I will take a negative. Right, other side I will take a negative for the measurement of rake angle. Right, here the rake angle, the inclination of rake angle is 0, and here please see the chip is moving along the rake face. The chip is moving along the rake face. Right, this is a chip which is moving along the rake face. Now see, please see the inclination. This is the rake face. Now see the inclination of the rake face. See the inclination of the rake face from the reference line. Okay, is that the, is that this one? Right, now this side will lie in the negative side. So I will call as a negative rake angle. Right, I will call as a negative rake angle. Now there is some important analysis, my dear. Here positive rake angle generally are what? Sharper. They are sharper. Positive rake angle are what? Sharp. Positive rake angle tool are what? Sharp. Okay, so that's why the required force and cutting velocity, that's why the required force and cutting velocity okay, is less compared to the 0 or negative rake angle, because it is a sharp. As the value of positive rake angle is going to be decreases, the sharpness of the tool is going to be decreases. So in that case, that is the less sharper than this, and this is less sharper than 0 rake angle. So overall you can say the negative rake angle is less sharper. Okay, the negative rake angle tool less sharper, right, less sharper. So the required cutting force, so the required cutting force and velocity is increases, right, is going to be what? Is going to be increases in the negative rake angle tool. My dear, as you know, what is the power? Just a minute. As you know, what is the power? Power is what? Power is cutting force, right, cutting force into cutting velocity. Am I right? Cutting velocity. So in the case of negative rake angle, cutting forces increases, cutting velocity is increases. So overall here the power in case of what? In case of negative rake angle. Okay, cutting power, or you can say cutting force is increases, right, and cutting velocity increases. So overall you can say, or which implies that power, because here cutting forces increases, velocity is increases, and that are going to be what? Multiply. So power is going to be increases in ample amount. What do you mean by ample amount? Very huge amount. Ample, the meaning of ample is very huge, right? Very huge. So the required power consumption in negative rake angle tool, okay, is very high. But the advantage of negative rake angle is that, please see the tip of the tool, right? Please see the tip of the tool. Let me show you again. This is the, sorry, now please see. Okay, please see. This is the cutting tool, right? Okay, now see here. This is a cutting tool. Now this is the tip of the tool. This is the tip of the tool, right? And this is what? This is, my dear, this is my dear, please see, this is what? This is a material behind the cutting edge. This is the material behind the cutting edge. This is a supporting material. Basically it is what? It is the supporting material. It is a supporting material. Okay, supporting material. Okay, supporting material behind the cutting edge of the tool. Similarly, please see here, behind the cutting point, right? Behind the cutting point, the supporting material in zero rake angle is little bit larger than in case of what? If you compare in case of positive rake angle. Now behind the cutting edge, if you compare the supporting material, in negative rake angle tool is more, overall is more if you compare to the other case. Now what is the role of supporting material? My dear students, because of supporting material, right, the cutting edge of the tool, because of supporting material, right, because of supporting material behind the cutting edge, what happened? Okay, supporting material behind the cutting edge. If the supporting material, my dear, please see, if the supporting material is large, means the behind the cutting edge, if the supporting material is large, then the tool is stronger. Tool is stronger in terms of okay, structurally and thermally. Right? So structurally it can bear a more amount of load, and thermally it can bear a more amount of what? More amount of temperature. But suppose that if the supporting material is less, then the tool is weak. Overall you can say tool is what? Tool is weak, structurally and thermally, right? So overall, if you compare, okay, these three tools, so the negative rake angle tool is what? Is stronger, right? The negative rake angle tool, I will write here, negative rake angle tool is stronger, right? Is stronger if you compare with the zero rake angle tool and positive rake angle tool. But the positive rake angle tool is what? Sharper, right? Sharper. So this is a basic difference in between this rake angle. So I hope this concept is crystal clear to you people. Now, my dear, now let's talk about the type of machining, right? Let's talk about the type of machining. Dear, here there will be a two type of machining, that is a orthogonal cutting, right? Orthogonal cutting and oblique cutting, right? And oblique cutting. So from the figure, right? From the figure, I think the cutting is going to be clear. This is, my dear, this is what? See here. This is the width of the workpiece. This is the cutting edge of the, this is what? This is the cutting edge of the tool. And here the cutting edge of the tool is perpendicular to the cutting velocity. But similarly, you can see here, this is the cutting edge of the tool, okay, and it is not perpendicular to the cutting velocity. For a better understanding, what I am going to do, I am going to remove the chip here so that you can see a better picture Okay, better picture of the tool and workpiece. And meanwhile, we are going to discuss the assumption of orthogonal. The assumption of what? The assumption of orthogonal cutting, right? For the assumption of orthogonal cutting. Now, let's discuss the assumption of orthogonal cutting, my dear. The assumption of orthogonal cutting is here the cutting edge of the tool, right? This is what, as you can see, this is the cutting edge. As you can see, this is the cutting edge. This is the cutting edge, right? And this cutting edge should be what? This is what? This is the cutting edge. This is what? This is cutting edge, right? This is cutting edge. This cutting edge should be perpendicular to the cutting velocity. Okay, this cutting edge, and this is what? This is the cutting velocity, that is V. That is V, right? So the first assumption is cutting edge of the tool is perpendicular to the direction of cutting velocity, right? So here the velocity is perpendicular to the cutting edge. And the second assumption is that the cutting edge of the tool should be wider than, my dear, should be wider than the width of the tool. Suppose the width of the workpiece. Suppose that this is what? This is the width of the workpiece. Suppose that this is what? This is width of the workpiece. W is what? W is the width of the workpiece. So here the width of the cutting edge, or the cutting edge, should be wider than the width of the workpiece, and it will be extended beyond on both sides. The cutting edge is wider than the workpiece width and extended beyond the workpiece on either side. Also, see, this is the similar thing now. Here you can see this is a width, this is what? This is, you can see here in a very simple manner, you can see here, please see, this is a figure. You can see here, this is what, my dear? This is the width of the workpiece, right? This is the width of the workpiece. And that width of the workpiece, okay, and this is the width of the what? Tool. And the width of the tool should be wider than the width of the workpiece, and it must be extended beyond on the both sides, right? Also, my dear student, also, please see, also here the depth of cut. Here the depth of cut, this is what? Depth of cut should be very small. Okay, this is what? This is the depth of cut, right? This is the depth of cut. This is what? This is the depth of cut. My dear student, this is, let me write down here. This is what? This is D, or this is D. That is a depth of cut. That depth of cut should be very small, right? That depth of cut should be very small if you compare with the width of the workpiece, right? Otherwise, what happen? I mean, if the depth of cut should be less than the width of the workpiece, it means the T0, that is the uncut chip thickness, is small. If T0 is small, then the removed chip has a less thickness, and the chip is going to be produced in a continuous manner, and the surface finish will be what? Good. And the surface finish will be what? Surface finish will be good. So I hope the two assumptions are crystal clear to both of you. The two assumptions are crystal clear to, okay, the two assumptions are very crystal clear. Now, let's move to discuss, okay, the next assumption. Whatever be the chip are going to be produces, in this case, the chip generate or the chip generated flow on the rake face of the tool. My dear, whatever be the chip, see, whatever be the chip is going to produce, it flow along the rake face of the tool. So VC is what? VC is the chip velocity. Here VC is chip velocity. Chip velocity, right? Velocity. VC is the chip velocity. I will draw the figure again. it is a three-dimensional figure. Okay, it is a three-dimensional figure, but I will draw this figure, okay, from my side again. See here. See, this is the basically two-dimensional figure, and here I am going to do a cutting operation. This is the tool, right? This is the tool. This is the tool, and the chip is going to be generate. This is the chip, my dear, right? This is the chip. See, this is a chip here. This is a chip which I am talking about, right? This is a chip. So this is what? This is the chip velocity. This is basically a chip velocity, that is VC, right? That VC should be perpendicular to the cutting velocity, I mean the angle in between the VC, okay, the cutting velocity, and see the chip generated flow on the rake face of the tool with chip velocity perpendicular to the, here it is not clear, perpendicular to the cutting edge. Sorry, it will be a cutting, okay, cutting edge. The chip velocity, that chip velocity should be, right? That chip velocity should be, this is the chip velocity, that is VC, and that chip velocity should be perpendicular to the cutting edge. This is the cutting edge, as you can see. This is the cutting edge, right? This is the cutting edge. This is what? This is the cutting edge. So chip velocity and the cutting edge should be perpendicular. Also the cutting velocity, also here the cutting velocity, also here the cutting velocity V, and the cutting edge should be what? Perpendicular to, okay, each other, right? Now let's move to the next point. My dear, whatever be the chip is produces should be flow in orthogonal plane. The question is, what do you mean by orthogonal plane? The last assumption, that is the chip should be flow in a orthogonal plane. Now you may be surprised, sir, what do you mean by the orthogonal plane? So don't worry, my dear, I will tell you the meaning of orthogonal plane in the orthogonal cutting in further discussion, right? Now let's discuss the geometry of single point turning tool, right? In single point turning tool, as you can see, this is a single point turning tool, right? This is the turning tool, okay, this is the turning tool. Let me show you. This is the cutting edge, this is the main cutting edge, right? And this is the end cutting edge, right? This is called as main cutting edge. This one, side cutting edge or principal cutting edge, side cutting edge, or sometime we call as principal cutting edge, right? This is what? This is end cutting edge. This is end cutting edge, right? Now this is what? This is the side cutting edge. Below the side cutting edge, this is the flank, or because it is below the side cutting edge, that's why we call as side flank, right? And in this view also you can see, this is what? This is the end cutting edge, okay, this is the end cutting edge. Now below the end cutting edge, this is a flank. I hope it is visible to you. This is what? This is a flank. Now this flank is lie below the end cutting edge. That's why we call this is what? End flank. Okay. Now, during cutting, what happen? Whatever be the chip, during cutting, what happen? Whatever be the chip is going to produce will flow along that face. Will flow along that face. So that's why this face, my dear, right? This face, or you can say this face, right? This face is called as rake face. Rake face, right? And this is a shank of the tool. This is a shank of the tool which is going to fix into the tool post, right? This is the length of the tool. This is length of the tool, and this is width of the tool. And the tool is placed on the base. So this is a base of the tool, right? This is a base of the tool. So basically, we are going to discuss the tool geometry of a single point cutting tool. My dear friend, cutting using a single point cutting tool can be affected by 6 angles of tool and the nose radius of the tool. The arrangement of all these in a particular order is called single point cutting tool nomenclature or designation, right? Or designation. So for that designation, the two systems are widely used in the context. A, that is a ASA system, American Standard Association. In this system, angles defined are measured with respect to 3 mutual perpendicular plane. Here you can see there will be a 3 plane. Okay, this is a plane number 1. This is what? A plane number 1, right? This is plane number 1. A plane that is perpendicular, a plane perpendicular to base, okay, and along the length of the tool, along the length of the tool, right? Now the next plane is this plane. This is a plane number 2. This plane number 2 is perpendicular to the base of the tool and parallel to width of the workpiece, right? Again, plane number 2 and plane number 1 are perpendicular to each other. The third plane is this plane. This is the third plane. A plane which is parallel to base. This is the base of the tool. A plane which is parallel to base and along the length of the tool. So my dear student, these 3 plane means plane number 1, plane number 2 and plane number 3 are mutually perpendicular to each other. So in this plane we are going to explain the 6th angle, right? I explain the 6th angle. Now the advantage of this, because the angles specified in the ASA system are measured with respect to 3 perpendicular plane. Okay, the understanding of angles and measurement of angle are become easier, right? But the disadvantage is that analysis of machining will be difficult. Yes, analysis of machining means the calculation of power. Okay, analysis of force, analysis of power will become difficult, right? So to overcome the disadvantages of ASA, here ORS has been defined. Okay, ORS system is orthogonal rake system, right? Orthogonal rake system. ORS means is what? That is orthogonal rake system. So in ORS plane, we are going to define all the angle for the analysis of force and power. Now, let's move to the next slide. Let me explain you, the tool, the feature of the tool one by one. Again, I am going to explain, my dear. This is what? This is side cutting edge, right? This is what? This is side cutting edge. In this view, I have placed the tool in different view so that you can see the tool in a easier manner, right? This is end cutting edge, right? This is end cutting edge. Am I clear? So let me write down here, this is side cutting edge, right? This is side cutting edge, right? And this is what? This is end cutting edge, end cutting edge. Now below the side cutting edge, there is a flank. As you can see, this surface is known as side flank, right? Below the end cutting edge, the surface is known as end flank. The surface is known as end flank, right? Now the chip will flow along this face of the tool, and you know where the chip is flowing, or where the chip is flowing, that surface of the tool is known as what? Rake face. Okay, rake face of the tool, okay. So this top surface is known as what? Rake face, my dear. This is what? This is the rake face, right? Rake face of the tool. And this is what? This is the shank. This is a shank of the tool, which is going to fixed in the tool post, right? Which is going to fix in the tool post, right? My dear student, here this thing is known as the length of the tool, right? This thing is known as, this is the length of the tool, right? This is what? This is the length of the tool, and this is the width of the tool. This is width of the tool, width of the tool, right? And this is what? This is length of the tool. This is length of the tool, right? This is length of the tool. Now I think all the basic thing are clear. And this is what? This is a tip of the tool. Okay, this is a nose, or you can say tip. So sometime we called as a nose of the tool, nose. Okay, this is nose of the tool, or you can say tip of the tool. So one by one I am going to discuss the plane. My dear, plane number 1. Okay, please see the plane number 1. This is a plane number 1, right? And you can see that here this is the side cutting edge, right? This is a side cutting edge, right? This is a side cutting edge, and you can see a plane, that is what? A plane number 1. This is my plane number 1, and please see, this plane is along the length of the tool. This plane is along the length of the tool, and this plane is perpendicular to the base. Please cut the tool. This is what? As you can see in a very easy manner, this is what, my dear? This is side cutting edge, right? Side cutting edge. This is side cutting edge. Now this is a plane number 1, which is along the length of the tool and perpendicular to the base of the tool. Now cut the tool in this plane, right? Now cut the tool in this plane. When you cut the tool in this plane, okay, or when you take the projection of the tool in this plane, please see, this is the overall projection. This will be the overall projection, right? This is the overall projection. This will be the overall projection, right? This is the overall projection. Now see the inclination of the rake face, right? Now see the inclination of the rake face. Now see the inclination of the rake face. From this line, the inclination of the rake face from this line is known as what? Back rake angle, alpha B. Right, that is back rake angle. This is back rake angle, right? Similarly, if in this plane, if you see the inclination of the end flank, the inclination of end flank, right? The inclination of the end flank, see, this is what, my dear? This is the end flank, right? See here, please see, please look into the figure. This is the overall tool, right? This is the overall tool. This is the overall tool. This is the overall tool. This is the overall tool, right? Now, if you see the inclination of end flank from this vertical line, this will be end clearance angle, okay? End clearance angle or end relief angle, right? End relief angle. So this will be end relief angle, right? End relief angle. So I hope this plane is clear. This plane number 1 is clear. Now see the another plane, right? A plane which is parallel to the, right? A plane which is, okay, a plane which is parallel to the width of the tool. Okay, I am going to draw here again, please see. I will take the, yes, this figure is more clear. See here, a plane which is parallel to the width. This is what? This is the width of the tool. This is width of the tool. Okay, this is width of the tool. As you know, I have already shown you, this is W is the width of the tool. Here, let's see, and this is a plane which is parallel, okay, a plane which is parallel to the width of the tool and perpendicular to the base of the tool. So this is what, my dear? This is basically, this is what? This is perpendicular to the base. So here, please see, in this plane, this is a complete plane. I am talking about this plane. This is a complete plane. That plane is parallel to the width of the tool and perpendicular to the base of the tool. Now see the inclination of, rake surface. Now this is the rake surface. Now see the inclination of rake surface from the horizontal line of this plane. This angle is known as side rake angle. So this is what? This is side rake angle. This is what? This is side rake angle. So I hope here side rake angle is little bit crystal clear to you people, right? Little bit crystal clear to you people. Okay, let me give you some detail of your back rake angle. Okay, this is a side rake angle, my dear. Here you have seen that this is the back rake angle. Now the back rake angle, it is an angle between, basically what? It is an angle between the face of the tool and base of the shank or holder, and it is usually measured in a plane perpendicular to the base, right? Perpendicular to the base and parallel to the length of the tool. Either you can remember the definition or either you can remember the thing, okay, with the help of this figure. I hope the thing is crystal clear. Now here, my dear student, it alpha B, that is a back rake angle, it affects the ability of the tool to shear the work material, okay, and form the chip, right? And form the chip. Here, in turning of long shaft, okay, generally we recommend in turning of long shaft, okay, which have very small diameter, we recommend a positive back rake angle. We recommend positive back rake angle, right? We recommend positive back rake angle. Now, let's discuss about the some points regarding to the side rake angle. Let's discuss some point regarding to the side rake angle. So what do you mean by the side rake angle, my dear? Side rake angle, basically I showed you what is a side rake angle. Side rake angle, it is the angle between the face of the tool and the base of the shank or holder, and is usually measured in a plane, and it is usually measured in a plane perpendicular to the base and the and parallel to the width, right? And parallel to the width. So this angle is crystal clear, I hope. Now suppose that this is a side rake angle. Now increasing in the side rake angle reduces the chip thickness, okay, and also the side rake angle controls the flow of chip. So let me write down some point regarding the side rake angle. Let me write down some point. Increasing the side rake angle, if you are going to increase the side rake angle, then the chip thickness, okay, then the chip thickness is chip thickness is what is going to be reduces. Increasing in side rake angle reduces the chip thickness in machining. Chip thickness reduces the chip thickness, because this tool generally used in turning operation. So in turning, right? So in turning also, that side rake angle is also control the flow of chip, right? That side rake angle is also control the chip. Clear? So I hope the thing is crystal clear. Now here one more angle is remaining, my dear. Please see this side flank. Please see this side flank here. There is a side flank. This is a side flank. I hope you are able to see. This is a side flank. Okay, this is a side flank. Is it visible? Now this side flank is in it is inclined. So the inclination of the side flank, the inclination of the side flank from this vertical line in this plane is known as side relief angle. Side relief angle, right? Side relief angle. This angle is known as what? Side relief angle. Okay. So, side relief angle, basically either if you talk about the side relief angle, or either you can talk about what? The end relief angle. Let me draw you the end relief angle again. This is, okay, this is what? This is the end relief angle. See, this is what? This is the end relief angle. This is what? This is the end relief angle, and this is side relief angle. My dear, here end relief angle you have measured in a plane which is perpendicular to the base and along the length of the tool. So either if you talk about the end relief angle and either if you talk about the side relief angle, both the angle basically avoid okay, rubbing of the respective plane with the workpiece. If rubbing is going to be avoided, then what happen? Then your friction is going to be what? Minimizes, right? Friction is going to be what? Minimizes. Now, so I hope both the thing is crystal clear. Now let's move to the next slide. My dear, this is the top view of this plane. Okay, this is the top view. Basically in this plane, a plane which is parallel to the base of the tool and along the length of the tool. In this plane, we are going to see, in this plane, This is the side cutting edge, my dear. This is the end cutting edge, my dear. Now in this plane, you are going to see the inclination of side cutting edge. Okay, the inclination of side cutting edge from the vertical line. So this is known as side cutting edge angle. So here the CS is side cutting edge angle. Side cutting edge angle. Side cutting edge angle, right? Side cutting edge angle. Now here, see, this is what? This is, as you know, this is the end cutting edge. Now the inclination of end cutting edge from this horizontal line which lie in this plane is known as end cutting edge. End cutting edge angle. End cutting edge angle. End cutting edge angle. End cutting edge angle. Right? Now see the next one, that is the tip of the tool. This is the tip of the tool. So we call this nose of the tool. So basically this nose has some radius that is called as nose radius, right? Nose radius. This is called as nose radius. This is called as nose radius. NR is the nose radius of the tool. Nose radius of tool. Okay, nose radius of tool. So this is a simple geometry. Side cutting edge, end cutting edge is crystal clear. My dear, the end cutting edge, the function of end cutting edge, the end cutting edge is not going to cut the workpiece. Basically, it prevents the trailing end of the cutting edge. It is a trailing end of the cutting edge. It prevents the trailing end of the cutting edge of the tool from rubbing against the workpiece. My dear, a larger end cutting edge angle weakens the tool. As you increases the end cutting edge, what happen? The tip becomes sharper. If the tip becomes sharper, then the supporting material is going to be decreases, right? So the tool become what? Weak. So the optimum value of end cutting edge angle is in between from 8 degree to 15 degree. Now let's talk about the side cutting edge angle. Now it is the angle which prevent interference as the tool enter the work material, right? As the tool enter into the work material. Normally the value of CS, right? This is a very important thing. Normally the value of CS will be lie in between 15 degree to 30 degree. This is the optimum value. This is the optimum value, my dear, right? This is the optimum value. Generally we keep this value for CS in this range. It doesn't matter, it doesn't necessary, or it doesn't mean that always the value of CS will be lie in this range. The value of CS may be less than 15 degree, or the value of CS may be greater than 90 degree, but for optimum condition we prefer, okay, from 15 degree to 30 degree. For good cutting condition we prefer for CS from 15 degree to 30 degree. Okay, so you know, if the value of CS is going to be increases, then what happen? The greater the component of force tending to separate the work and the tool material. Let me show you. Suppose that generally you have seen that this type of tool is going to be used in turning operation. This is the turning, okay, turning operation. You can see turning operation. This is the turning operation, okay, turning operation. It is clear. Now in turning operation, the workpiece is rotating with RPM n, that is revolution per minute, having a diameter, okay, having a diameter that is D. Oh my god, having a diameter that is having a diameter that is what? That is D, right? This is the diameter of D, right? D. Now here see here, this is the machine surface. So this is the diameter which is obtained after machining. Okay, so here this is what? This is the depth of cut. This is what? This is depth of cut, right? This is small d, that is depth of cut. I think it is not visible, so I will use another color. This is depth of cut D. Okay, this is depth of cut. Depth of cut is what? How much tip of the tool is perpendicular inside from the surface of the workpiece. So this is the depth of the tool. My dear, you have given the feed, okay, to the tool in this direction. This is feed, that will be in mm per revolution. Mm per revolution, right? The feed is given to the tool parallel to the feed is given to the tool parallel to the axis of rotation. This is what? This is the axis of rotation, right? This is axis of rotation, axis of rotation, axis of rotation. Now here the feed is parallel to the axis of rotation. The tool is coming in this direction. Per revolution the tool is coming, okay, some amount, that is in the mm, okay, in a linear. So when the tool is coming in this direction, you can see the tool is in contact with the workpiece along this line. So this line is known as line of action. Okay, line of action. This line is known as line of action. I'm not going to write. Now, my dear friend, because this is the line of action, and along this line of action, okay, the tool and workpiece are in contact. So the thrust force will always be perpendicular. So the thrust force will always be perpendicular to the line of action. So this is a thrust force, right? This is the thrust force, that is Ft, that is Ft, thrust force, right? Thrust force, thrust force. My dear, suppose that in this machining, let's say this is the x direction and this is y direction, right? This is the x direction and this is what? This is y direction. So here you can see that Ft, that is a thrust force, either it is this is not acting in the x direction, nor in y direction. So basically you can write or fxy, right? fxy. Now one more thing, this is the component. This is basically, this is a line. Okay, now see here, this is what? This is a side cutting edge, right? This is a side cutting edge. Now see, if you take the component of Ft, if you take the component of Ft, my dear, if you take the component of Ft along the axis of rotation and across the axis of rotation. Now, my dear, this is Cs, then this is Cs, this is 90 minus Cs, then this is what? Cs, right? This is what? Cs. Now, if you take the component, then this is what? Ft, right? This is what? This is Ft cos Cs. This is what? Ft cos Cs. And this is what? Ft sin Cs, right? Ft sin Cs. Now, if you increase the value of Cs, we are talking about that if you increase the value of Cs, suppose that if you are going to increase the value of what? Cs, right? If you are going to increase the value of Cs, you are going to increase the value of Cs. Then what happened? Cos Cs, here what happened? Cos Cs is going to be decreases, yes or no? And the sin Cs is going to be what? Increases. Sin Cs is going to be increases, and sin Cs is going to be multiplied with Ft. So this force is known as, my dear, radial force, and this Ft cos Cs is known as feed force or this force is known as axial force, because that the component of thrust force is acting along parallel to the axis of rotation. So that's why we call axial force or feet force. Now if you increase the CS, then what happen? Cos CS is going to reduces. So overall feet force or axial force is going to be reduces. Okay, means the separation, the tendency of separation. Okay, the tendency of separation of the tool from the workpiece along the x-axis is going to reduces, but the tendency of separation of the tool from the workpiece is going to increases in the radial direction. Okay, in the radial direction. Right, so this is a problem. This is a problem if you are going to increase the value of what? Increase the value of CS. Okay, increase the value of CS. My dear, at its increased value, it produces a thinner and wider chip that will distribute the cutting head. So you can say it is going to increase the tool life. Also, there is an exception, that a zero side cutting edge angle. What? That is a zero side cutting edge angle, CS, when it is a zero. Okay, in which case CS will be take 0. It is a special case. Zero side cutting edge angle is desirable when machining casting, when machining of a casting and a forging with a hard and a scaly skin, because of the least amount of tool. In that case, what happened? The least amount of the tool is going to expose or comes in a contact with the workpiece, and if the least amount of the tool comes in a contact with the workpiece, then the less length of action is going to be what? Deteriorated, right? So this is the overall analysis of side cutting edge angle, and side cutting edge angle is the most important thing. Also, by increasing the side cutting edge angle, please remember, by increasing the side cutting edge angle, the cutting force and the power is not going to be what? Increases. The power is not going to be what? Is increases, right? This is a very important thing. This is a very important thing. By increasing the side cutting edge angle, your cutting power consumption, okay, or cutting force are not going to be what? Increases, right, my dear student? Now let's discuss some other extra point. Let's discuss some other extra point. What is that? The next thing is that the nose radius, right? The nose radius. Let's discuss about the nose radius. Little bit about the nose radius. Let's discuss about the nose radius, right? This is a tool you have seen. This is a side cutting edge, right? And this is the end cutting edge. Right? Now see. This is the nose radius. This is the nose radius. This is the tip of the tool. Okay, nose of the tool. Nose. So that nose had some curvature, and that curvature has some radius. That is a nose radius, right? That is what? That is the nose radius. Nose radius. That is the nose radius. Now that nose radius, it is a curvature of the tool tip, right? It is a curvature of the tool tip. It strengthens the tool, okay, nose, by reducing the stress concentration. More the curvature comes, more the more the stress concentration is going to be what? Okay, stress concentration is going to be reduces. So overall the tool become what? Stronger. So the overall the tool become stronger. Also it provide a better surface finish, because the surface roughness, that is the average roughness, that is the roughness, average roughness. Okay, that is what? That is the average roughness, average surface roughness, average surface roughness, average surface roughness equal to F square by 8R. F is what? Here F is feet of the tool. Feet of the tool, right? And Rn is nose radius. Nose radius. My dear, if you keep feet constant, if you keep feet, here it is a F square. This is what? F square. If you keep feet constant and if you increase the nose radius in the denominator, so overall average roughness is going to be what? Decreases, which implies that surface finish of workpiece is increases. Yes or no? Overall surface finish is going to be what? Increases, right? So this is the importance of what? This is the importance of nose radius. But we have to keep the nose radius in an optimum range. Okay, too large a nose radius, too large, if you keep the nose radius too large, then what happen? It will induce chatter. It will induce chatter, right? And if the nose radius increased, what happened, my dear? If the nose radius is increased, then the cutting force and cutting power is also going to be increased. So please remember this point. If nose radius increases, which implies that cutting force and power increases, right? Increases. Cutting force and cutting power increases. This is a very important point. Okay, from the nose radius point of view. So we have to keep the nose radius in a optimum condition. Otherwise what happen? Okay, otherwise chattering will be happen, right? Also my dear, if you increase the nose radius, what happen? Tool life is increases, right? If you increase the nose radius, then tool life increases. Okay, tool life increases. Why tool life increases? Because stress concentration on the tip of the tool is going to be what? Reduces. Okay, because the stress concentration, okay, the stresses which comes on the tip of the tool, stress concentration is going to be reduces while cutting if you increase the nose radius. Okay, if the stress concentration is going to be reduced, then the tip of the tool become what? Increases, right? Now the designation, tool designation, according to what? According to ASA, right, my dear? The tool designation according to ASA, right? Now here, according to this ASA, okay, the rake system comes first, and the relief system, and then cutting system, and it will end with nose radius, and it will be generally keep in inch, right? So according to this system, what we do? First of all, we write rake system, then relief system, right? Then cutting system, then end with nose radius in inch. In each system, you have to write side in the end, side in the end, side in the end. In each system means what? In a rake system, you write side in the end, relief system side in the end, cutting system side in the end, and write down the remaining one, that is a back rake angle, and relief angle, and cutting edge. And the nose radius generally will be in the inch, according to the ASA rule, right? But as you know, according to ASA, understanding of 6 angle and nose radius, according to ASA, understanding of 6 angle and nose radius will be easier. but the analysis become very difficult according to ASA. What do you mean by the analysis? The calculation of power, right? What do you mean by the analysis? The calculation of power and force become very difficult, right? Become very difficult. For that, we recommend ORS system, that is orthogonal rake system. Here, at the first place, I will become, I is the inclination angle. I is the inclination angle. Now I will tell you the meaning of the inclination angle. My dear, you have seen here, right, in the orthogonal machining or oblique machining, okay, which I have discussed under the heading of type of machining, right? My dear, what is the inclination angle? Let me explain you, right? As you can see, the cutting velocity is acting in the x direction, the cutting edge is lie on the y direction, and this is the z direction. Now see, the cutting edge lie along the y axis in orthogonal cutting, okay. The cutting edge is lie along the y axis in orthogonal cutting, but my dear, but suppose that if you talk about the oblique cutting, right, if you talk about the oblique cutting, this is what basically, this is basically, my dear, please see, this is basically, this is the y axis, right, this is the x axis, right, see here, this is the y axis, this is the x axis, sorry, this is what, this is the y axis, right, this is the y axis. Now see, this is the x axis, right? See, this is the y axis, this is the x axis, and this is the z axis, okay. This is what, this is the z axis, this is the z axis, right? See, the inclination of the cutting edge from the y axis is here is what, 0, but here the cutting edge of the tool, but here the cutting edge of the tool, right, but here the cutting edge of the tool, right, is inclined from the y axis, and it is not equal to 0. It has some value. So I is basically a inclination angle, right, inclination angle. My dear friend, generally in orthogonal cutting, the value of I is 0, right? The value of I is 0. If I say that the cutting is orthogonal, that you have to select that I is 0. But suppose that if you say I is 0, it means that it is an orthogonal cutting? No. Vice versa is not true, right? If you say orthogonal cutting, then I is 0. If you say I is 0, it doesn't mean always that the cutting is orthogonal, right? It may be a oblique cutting, right? But if I say a cutting is a orthogonal, so you have to always consider that I is what, 0. So you have to always remember that what is I is the inclination angle, right? I is the inclination angle. I is what? I is the inclination angle in a orthogonal rake system. Alpha is a orthogonal rake angle. It is the overall angle of back rake angle and side rake angle. And here at the third place, it is the side relief angle. It is the side relief angle. And at the fourth place, it is the end relief angle. And at the fifth place, it is a end cutting edge angle. And at the sixth place, it is the approach angle or principal cutting edge angle. My dear, if I draw the tool, this is the tool, right? This is the tool, and this is what? This is see, this is what? CS, right? This is what? This is CS. Now, see this line, this is what? Perpendicular, okay? Now, this angle is known as approach angle, lambda, that is 90 minus CS. Lambda, that is 90 minus CS. It is also called as principal cutting edge angle or approach angle, which is 90 minus CS. And at the end, we are going to what? Nose radius, that is R. Generally, we keep nose radius in mm in orthogonal rake system. Again, I tell you, if it is given that orthogonal cutting, then I is always 0. But in oblique cutting, I is never 0. But if I is 0, it doesn't mean that the cutting is orthogonal. Also, instead of, if I say one statement, if I say orthogonal cutting, right? Orthogonal cutting. Or instead of, I will say chip flows in orthogonal plane. Orthogonal plane. What does that mean? The meaning is same. The meaning of both the statement is same. Orthogonal cutting or chip flow in orthogonal plane, it means it is a orthogonal cutting. In both the case, you have to take inclination angle as 0. You have to take the inclination angle as what? The inclination angle is 0. Right. Now, sometime question will become on the basis of interconversion. Right. Sometime question will become on the basis of interconversion. Now, interconversion between AS and ORS, tan alpha. Suppose it is a tan alpha equal to tan alpha S into sin lambda plus tan alpha B into cos lambda. Tan alpha B equal to cos lambda into tan alpha plus sin lambda into tan I. Tan alpha S equal to sin lambda into tan alpha minus cos lambda tan I. Tan I equal to minus tan alpha S cos lambda plus tan alpha B sin lambda. Now, you have to remember this. Now, the smart thing, okay, by a smart approach, you can learn this formula. Please see those this two formula. Please see this two formula. There are some common thing like tan alpha S, tan alpha S, tan alpha B, tan alpha B. Right, right. And this is a sin lambda cos lambda and minus cos lambda sin lambda. So what to do? Do one thing. Sin lambda cos lambda, take a integration of take a integration of sin lambda, it comes sin lambda. Integration of cos lambda is what? Sin lambda, right? Now multiply it with it is a square matrix of that. Multiply the column matrix of tan of alpha S and tan of alpha B. Tan of alpha S, that is side rake angle, and tan of alpha B that is a back rake angle. It gives you a column of tan of alpha and tan of I. That is, if you multiply that row into column, you will get tan of alpha. If you multiply that row into that column, you will get tan I. Right? In a similar fashion, please see these two formula. These two formula, please see. What are the common thing? Tan alpha, tan I, and cos lambda, sin lambda minus cos lambda. So what to do? What to do? Here you have started, initially you have started from sin lambda, na? Write down initially from cos lambda. The next one will be the opposite of the previous one, that is a sin lambda. In the next row, write down the integration of the above row. Integration of cos lambda is sin lambda, integration of sin lambda is cos lambda. Multiply with tan of alpha and tan of I, that is a column matrix. You will get tan of alpha B. How? When you multiply this row into this column, you will get tan of alpha S when you multiply this row into that column. So it's up to you by which manner you can learn this formula. Right? It's up to you by in which manner you want to learn this formula. Am I clear? I hope the point is crystal clear. Now, let's move. Okay? Now let's move. Now, this is a question which was asked in GATE 2008, right? Which is purely based on this question. Let me read it by step by step. What it say? single point turning tool, side rake angle and orthogonal rake angle are equal. He says that condition number 1, that side rake angle and orthogonal rake angle are equal. Okay. Phi is the principal cutting edge. Phi, principal cutting edge generally denoted by lambda. So I will take second lambda, that is a principal cutting edge angle, right? Principal cutting edge angle. Okay, it is given, but here the presentation is in phi. I am going to write in terms of lambda. Okay, and its range is given to you from 0 to 90 degree. The range is given to you 0 to 90 degree, right? 0 to 90 degree. Okay. Now the chip flow in orthogonal plane. My dear, the chip flow in orthogonal plane. What I told you, whenever he says that the cutting is orthogonal, whenever he says that if the cutting is orthogonal or chip flow in an orthogonal plane, what you should take, that inclination angle is what? 0. Right? The inclination angle is what? 0. You have to find the exact value of phi, that is lambda is closest to. Now you remember the formula. Okay, do you remember the formula? Here back rake angle and side rake angle are what? Equal. Okay, so you have to select that formula in which your alpha is alpha, okay, lambda and I will becomes, right? So you have to select that formula. So alpha s. Okay, so I think this formula is correct, more suitable, that tan of alpha s equal to sin lambda tan alpha, sin lambda tan alpha minus sin lambda tan alpha minus cos lambda tan I minus cos lambda tan I. My dear, here I is 0. So this is going to be what? 0, right? So here tan of alpha s equal to sin of lambda tan of alpha. It is given that alpha is equal to alpha, so tan of alpha is equal to what? Tan of alpha, it will be cancelled, which gives sin lambda equal to 1. So 1 will be exist in this range only when lambda equal to 90 degree. When lambda equal to 90 degree, so D will be the correct answer, right? So D will be the correct answer. So I hope the question is a little bit clear to you. Let's move to the next point. The next point is a very, very important, my dear. It's a very, very important. Yes, it's a very important. Many times in the GATE exam, the value of shear angle will be asked. Phi is what? Phi is the shear angle. Many times the value of shear angle is going to be asked in the GATE exam. So you have to remember, right? So you have to remember the formula. The R is what? R is a chip thickness ratio. R is a chip thickness ratio, and it is equal to T naught by TC. T naught is what? T naught will be the uncut chip thickness divided by chip thickness equal to LC by L. LC by L is the length of the chip divided by uncut length of the material equal to VC by V. VC is the cutting velocity of the VC is the chip velocity, and by V is the cutting velocity equal to sin phi by cos phi minus alpha. You can derive this in a very easy manner, but as you know, derivation generally doesn't come in the GATE exam. You have to learn the formula, right? You have to learn the formula. Okay, you have to learn, my dear, the formula. Formula is more important than the derivation. Now, by using R equal to, okay, by using R equal to sin phi divide by cos of phi minus alpha. By rearranging this, you will get this formula. That is tan phi equal to r cos alpha divided by 1 minus r sin alpha. Right? R cos alpha divided by 1 minus r sin alpha. This is a very important formula. This is a very important formula. Both the formula are very important. Right? Now, both the analysis or both the relations are valid in the orthogonal plane. Yes, both the relation are valid in orthogonal plane or cutting. Orthogonal plane or cutting, right? As you know, TC is more than T, right? As you know that TC TC is more than T naught, because after cutting the thickness of chip is going to be increases. So the value of R will be less than what? Less than 1. The inverse of R, that is H, sometime it is called as a inverse of chip ratio or a chip reduction factor or a chip compression ratio. That chip compression ratio is greater than 1, right? Is greater than 1. My dear, R basically is what? R, it is the index of the amount. It is the index of the amount of plastic deformation which the metal into the chip has undergoes. Right? Now, let's move to the next slide. Okay, let's move to the next slide. Before that that slide, if you know the shear angle, if you know the rake angle, okay, or if you know the R, then you can derive, then you can find out the value of what? Shear angle. You can find out the value of shear angle. Now, let's solve this question, my dear. Let's solve this question. During the orthogonal cutting of mild steel with a 10 degree, right? Here, alpha is what? 10 degrees given. Rake angle. The chip thickness ratio was obtained as, that is what? R, that is 0.4. The shear angle, evaluate from this data. You have to find the shear angle, right? You have to find the shear angle. Now, my dear, you know the value, you know the formula, that tan phi equal to r cos alpha divided by 1 minus r sin alpha. Now, you can find the phi, that is tan inverse r, that is 0.4 cos alpha, that is what? 10 degree divided by 1 minus 0.4 sine of 10. Now, by using the calculation, you can easily get the value and it will become 22.94, right? Now, let's see the next question. Next question was asked in GATE 2011, right? GATE 2011. What was the question? The question is very simple. A single point cutting tool with 12 degree rake angle, that is alpha equal to 12 degree, right, is used to machine a steel workpiece. The depth of cut, he says, the depth of cut, okay, that is the depth of cut, that is uncut thickness, that is uncut thickness, right? The uncut thickness is what? Is 0.81 mm. The depth of cut, that is uncut thickness, is 0.81 mm. The chip thickness, right? The chip thickness, the chip thickness is given to us, that is what? The chip thickness is what? Thickness, the chip thickness under orthogonal machining, okay, 1.8 mm under orthogonal, okay, under orthogonal machining, okay, under orthogonal machining. So alpha is given, depth of cut, that is uncut thickness. Let me show you what he is saying to us. Let me show you. Basically, see this figure, right? Let me show you the figure. What he says, see this, a depth of cut, right? A depth of cut. See this figure. A depth of cut T, okay? Depth of cut, that is what? That is the depth of cut. That is what? T0. So depth of cut and T0 is what? Same in orthogonal machining. Okay. So please remember that depth of cut, that is T0, is same in orthogonal machining. Now let's move to our question. Yes. So it is given to us. Now we have to find what? We have to find, my dear, the value of shear angle. Okay. Now we know that tan phi equal to r cos alpha divided by 1 minus r sin alpha. Now r is what? Chip thickness ratio, that is T0 by Tc, right? T0 by Tc. So T0 is what? The chip thickness T0. The depth of cut, that is uncut chip thickness, that is 0.81 divided by Tc, the chip thickness, that is 1.8. All the value are in mm. So what will be the chip thickness ratio? 0.81 divided by 1.8. It will become 0.45, right? Now phi equal to tan inverse alpha. Alpha is what, my dear? 12 degree cos, alpha. R is what? 0.45 cos alpha, that is 12 degree, divided by 1 minus 0.45 sine of 12. So what will be the answer? Answer into cos of 12, okay, cos of 12 divided by 1 minus answer into sine of 12, shift tan inverse, it comes 25.90. So 25.9011 degree. So approximately it is what? 26 degree. Approximately it is what? 26 degree. Okay. So it's a very simple question. Let's move to the next topic. The next topic, or let me solve one another question. See here. Okay, we will solve some other question. I mean, let me cover something, some theory. Then we are going to solve some other question also. So, what do you mean by cutting shear strain? My dear student, what do you mean by cutting shear strain? The cutting shear strain, basically the magnitude of strain that is developed along the shear plane due to machining action is called cutting strain. The relation of the cutting shear strain E, okay, is what? That is cot phi plus tan phi minus alpha. Suppose that this is your tool, okay. Let me just cover this. Just forget this one, okay. Just forget this one. Now suppose that initially the tool is here. This is a position of tool. Okay. Now this is the initial position of the tool. When the tool comes from here to here, then what happened? When the tool comes from here to here, you know this is AB, that is a shear plane. When tool tip comes from here to here, then along the shear plane, what happened? That is in a primary deformation zone. This is what? This is a primary deformation zone. In primary deformation zone, what happened? Because a shear force is going to act, and because of that shear force, deformation is going to be happen. That A will become, okay, that A will become at this point, that is A dash, when tool comes from here to here, right? When that A will comes from here to here, let's say it is A dash, and that B basically, look, and that B will come from here to here, right? That B will come from here to here. So the system will look like this. So A dash or B dash is, you know, lateral displacement, right? Lateral displacement. That B dash equal to A dash. That is, let's say, delta X. This is known as, let's say, delta X. What? Delta X, right? So if delta X divide by the perpendicular distance, my dear student, the perpendicular distance, okay, this is the perpendicular distance, okay, let's say perpendicular distance is, let's say, L, okay, let's say perpendicular capital L, okay, capital L, this is the perpendicular distance, capital L will give you what? Will give you shear strain, right? Will give you a shear strain. When you solve this equation, okay, in terms of alpha and phi, the derivation, again, the derivation is not important to you, but I am giving you little bit flavor of the shear strain, okay? When you come to my regular classroom, then I will give the detailed derivation, okay? So delta X by L, when you derive this thing, when you, okay, resolve this thing, you will get cutting shear strain. You will get cutting shear strain equal to cot phi plus tan phi minus alpha. So you have to remember this relation. This relation is very important for you people, right? This relation is very important to you people. Now, suppose that, my dear, one question is that, suppose that if alpha is, okay, if alpha is 0, if alpha is 0, okay, let me see, this is a cot phi plus tan phi minus alpha. If alpha is 0, okay, then what will be the cutting shear strain value? Then cutting shear strain, that is what? Cot phi plus tan of phi minus alpha, that is what? 0. So cutting shear strain equal to cot of phi, or suppose that if I assume that tan phi is equal to what? Let's say it is x, so it will be 1 by x, okay? So what will be the minimum value, right? What will be the minimum value? My dear, I will use a one simple relation, that is, I will use arithmetic mean and geometric mean. Suppose that if you take the arithmetic mean of this, what will be the arithmetic mean? Arithmetic mean of this, x plus 1 by x divided by 2, and what is the geometric mean? X, okay, x into 1 by x, okay, this, right? So generally this will give you a relation, and the minimum value of cutting shear strain will be what? 2. The minimum value of cutting shear strain will be what? Will be the 2. So always remember, the minimum value of the cutting shear strain is 2 when alpha equal to what? 0. What I use the arithmetic mean and geometric mean relation, right? Arithmetic mean and geometric mean relation. I use that relation, right? I use that relation. Now, the next thing is that velocity in metal cutting. My dear student, let me explain you the concept of velocity in metal cutting. Before that, suppose that this is the, suppose that This is the tool, right? This is the tool, and this is the chip. This is the chip, right? This is the chip. Okay. So I am going to again rearrange the thing. Don't worry. Again, I am going to rearrange the thing. This is the tool. See, right? And okay. See here. This is the tool, and this is the chip which is going to be produced here, right? Which is going to be produced here. Now, suppose that tool is coming with a cutting velocity v, that is horizontal to the that machine surface. This is the shear plane. A, B is the shear plane. It makes an angle phi, and this is this is what? T0, that is uncut chip thickness, and it is equal to D. Now, this is a V. Okay, my dear. Now, this is a cutting velocity. V is what? Cutting velocity. So, all the velocity which comes in a picture in the cutting are relative velocity. This is a V, that is a cutting velocity of the tool with respect to workpiece, right? Cutting velocity, that is a velocity of chip, right? That is a velocity of chip, right? And that is the shear velocity, that is a shear velocity. My dear, what is VC basically? VC is chip velocity, right? Chip velocity. Chip velocity. My dear, that chip velocity basically velocity of chip with respect to tool, right? Velocity of chip with respect to what? Tool. Vs, that is the shear velocity. That is shear velocity. Okay, what do you mean by the shear velocity? It is pretty simple. You have seen that this shear will be occur in that plane, that is a delta x. Now that delta x, that shear, that delta x, that lateral displacement per unit time will give you what? Shear velocity. And how can you observe? Suppose that if you are standing here, suppose that if you are standing here, then you can see with your eyes, then the deformation will occur, okay, in this plane when you are observing, okay, with respect to the workpiece. That delta x means that a dash equal to that b dash equal to that delta x will occur when you observe this thing with respect to the workpiece. Now, so my dear student, so my dear student, that shear velocity you can observe when you are standing, okay, on workpiece, okay, with respect to workpiece. So velocity, this is what? This is the deformation of chip with respect to what? With respect to WP. Here WP stand for workpiece, right? Now V, that is the tool or cutting velocity. That is the cutting velocity. That is a cutting velocity. This is also relative velocity. This is what? This is a velocity of tool, right, with respect to what? Workpiece. So all the velocity are what? All the velocity are, my dear, relative velocity. One thing is also there. One thing is also there. This is what? This is a reference line. This is a reference line, or you can say a normal line. This is a alpha. This is a shear angle. Now with the help of this, we are going to make what? We are going to make a triangle. Now this is a V, okay. So this is a V. Now I'm going to make a triangle. So look, V, it is a horizontal. This is a V, right? This is a V. This is the cutting velocity V. Now this is what? VC, okay, and this is VS. VS is along the shear plane. It means it makes an angle phi from the horizontal, and along the horizontal there is a cutting velocity. So my dear student, this is what? This is your VS. This is your VS. It makes an angle phi with the cutting velocity. Now, there is a reference line. There is a reference line, my dear student. See here, this is a reference line, right? And see, this is a chip velocity, VC. This is a chip velocity. This is the chip velocity. That is what? That is VC. It makes an angle alpha, okay? VC. Basically, it makes an angle alpha with the reference line. So, it makes an angle alpha from the reference line. So, it is what? It is 90 minus alpha, and let's say it is x. Can you find the value of x? Yes, we can find the value of x. How can we find the value of x? Because we know that the sum of the triangle, the sum of the angle of the triangle, that is angle of x, that is your 90 minus alpha plus, okay, this is what? This is angle x. Okay, 90 plus alpha and plus phi equal to what, my dear? 180 degree. So what will be the value of x? That is 90 minus phi plus alpha, or you can write 90 minus phi minus alpha, right? This is the value of what? This is the value of x. Now you have to apply, okay, you have to apply a theorem, that is a sine theorem. What is the sine theorem? Lami's theorem. You have to apply the Lami's theorem. Now let me tell you the Lami's theorem. What Lami's theorem will say? Let me make a copy of this. Okay, let me make a copy of this. This is the, okay, now see here, see. Now I'm going to remove this, I'm going to remove this, I'm going to remove this, I'm going to remove this. Also I'm going to remove this, right? Now what was x? X equal to 90 minus phi minus alpha. Okay, write down the Lami's theorem. What did it say? Sine of this angle, okay, or opposite side, that is cutting velocity, divide by opposite angle of sine, that is sine of x, equal to opposite equal to that side divide by sine of phi, that is VC divide by sine of phi equal to VS divide by sine of this. Okay, VS divide by sine of 90 minus alpha. Now my dear, V divide by sine of x minus x, sine of x equal to 90 minus phi minus alpha. So I can directly write it is a cos of phi minus alpha. VC divide by sine of phi equal to VS divide by sine of 90, not a sine 9 of 90. You can also write cos of alpha, right? Cos of alpha. So this is a very important relation. For your exam point of view, this is a very important relation. Some student may face difficulty to remember this relation. So I recommend that you should remember this triangle. Okay, if you remember this triangle, then easily you can derive this relation. Okay, easily you can derive this relation. So I hope the point is crystal clear. Now let's move to the next concept. That is what? That is your shear strain, right? That is your shear strain rate. Now dear, what do you mean by the shear strain rate? Shear strain rate, it is the strain per unit time, right? It is a strain per unit time. It is not a shear strain, it is a rate of shear strain. That is a flow, that is a strain per unit time. So strain per unit time, when you derive this relation, it comes shear velocity, divided by thickness of the shear zone. Thickness of the shear zone means that is the thickness of the shear zone. Okay, that is the thickness. Okay, just forget this thing. Okay, that's just forget this thing. Thickness of the shear zone is, that is the thickness of the shear zone, right? That is the thickness of the shear zone. That is what? That is TS. that is TS, thickness of the shear zone. So shear strain rate equal to, okay, you can write strain per unit time, small strain per unit time, or shear velocity divided by thickness of the shear zone, right? Thickness of the shear zone, okay, thickness of the shear zone. Sometime thickness of the shear zone is not given in the exam, so you have to remember that the thickness of the shear zone, okay, thickness of the shear zone can be taken as, thickness of the shear zone can be taken as 25 micron, can be taken as 25 microns, right? Or it will be taken as 1/10 of the shear plane length and 1/10 of the shear plane length, okay, 1/10 of the shear plane length. Clear? Now let's move to the next one, okay. Or it will be beneficial that if we are going to solve some question, right? It is beneficial that if we are going to solve some question. Now I'm going to write some question. Let me write a question. That question was asked in GATE 2012. That question was asked in GATE 2012. What was the question? Question is detail pertaining to an orthogonal metal cutting process. There is a metal orthogonal cutting, okay, metal orthogonal cutting is given, orthogonal cutting is given. I think it is it will be not clear, it will be not clear, okay. I will use a pencil. Orthogonal cutting operation, orthogonal cutting is given. In orthogonal cutting, it is given that chip thickness ratio, that is R, is given. What was R? 0.4. 0.4 is given, right? Undeformed thickness, that is what? T0 is given, that is 0.6 mm, okay, 0.6 mm. Again, rake angle is given, that is alpha, rake angle alpha is given. How much? It is 10 degree. Let's say it is a 10 degree. And your cutting speed your cutting speed is also given. What was the cutting speed? It is 2.5 meter per second, 2.5 meter per second, and the thickness of the shear zone is given 25 micron. It's given 25 micron, right? It's given 25 micron. Now you have to tell me shear strain rate. What will be the shear strain rate? We know that cutting shear strain rate is Vs divided by Ts. We know the value of Ts, but we don't know the value of what? Vs. So how can we find that Vs? It's a very easy. How can we find the value of that? Okay, that Vs. Now just see, how can you find the value of Vs? Now Vs, for Vs you have you know the value of cutting speed, that is V, okay, and you know the value of what? You know the value of what? You know the value of R, you know the value of alpha, okay. By applying the triangle, okay, formula or triangle relation, you can find the value of Vs, but for that we need a value of shear angle. So my dear, what will be the R? Okay, what will be the okay, your phi? So phi equal to what, my dear? Phi equal to 10 inverse R cos alpha divided by 1 minus R sin alpha, right? So phi equal to, let me calculate. So R, that is 0.4, 10 inverse 0.4 cos alpha, that is 10, divide by 1 minus 0.4 sine 10, right? Phi equal to tan inverse 0.4 into cos 10 divided by 1 minus 0.4 into 0.4 into sine 10. So it comes shift 10 inverse answer, it comes 22.94 degree. Now this is the value of phi. Now you know the value, you know the relation, that is a relation, okay? You know the relation. Where was the relation? This is the relation, V divided by cos of phi minus alpha and Vs by cos of alpha, right? So V divided by cos of phi minus alpha, V divided by cos of phi minus alpha, V divided by cos of phi minus alpha equal to Vs divided by cos of alpha, right? Vs divided by cos of alpha. Clear? Okay. Now, can you find the value of Vs? Yes, we can find the value of Vs. What is the Vs? Vs is V into cos of alpha divided by cos of phi minus alpha. Vs equal to 2.5 cos of alpha, that is cos of 10, divided by cos of 22.94 minus 10. So you will get the value of what? You will get the value of Vs. So what will be the value of Vs? Let me calculate. That is cos of 10 divided by cos of answer minus 10, answer into 2.5. It comes 2.526, 2.526, right, in meter per second, Now what is a cutting shear strain rate? Cutting shear strain rate, that is Vs divided by Ts. So Vs, as you know, 2.526 divided by 25 into 10 to the power minus 6, it will become per second. Answer divided by 25, so it will become cutting shear strain rate 1.0104 into 10 to the power 5 per second. Okay, so this is your final answer. I hope you understand the concept of cutting shear strain, right? I hope you understand the concept of cutting shear strain. There are a lot of other questions, right? There are a lot of other questions. Now let's discuss let's discuss about the turning. Let's discuss the turning analysis. You know, in the turning operation, this is the initial diameter of the workpiece. You know, in the turning operation, this is what? This is the initial diameter, okay, and this is the diameter which produce, this is the diameter which produce which is produced after machining operation, right? Which is produces after machining operation, which is produced after machining operation. This is what? This is the initial diameter. Let's say it is a D0, okay? Let's say it is a D0, and this is the diameter which is produced after machining. After machining, let's say D final. Now, this is a tool, and the workpiece is rotating with RPM n revolution per minute, and the feed is given to the tool. This is the axis of rotation, right? This is the axis of rotation, and this is what? This is the feed. This is the feed, okay, of the tool. This is a feed that is in mm per revolution of the tool is given to the tool. Now, suppose that in turning operation, okay, in turning operation, dear student, in turning operation, first of all, we have to understand some forces. This is the axis of rotation, right? This is the axis of rotation. Now, let's say this is what? X-axis, let's say, this is y-axis, and let's say this is z-axis, right? This is x-axis, the axis which is along the axis of rotation, y, the axis which is perpendicular to the axis of rotation, and this is z. Now there will be a cutting force which is acting, okay, this is the cutting force, actual cutting force, which is acting in the, okay, in xy,z. Now take the component of that cutting force in xy plane, that r is acting in a space. Now take a component of that r, okay, of that r in a xy plane. Now this is the component of what? This is the component of what? This is a component of your r in xy plane. This is known as what? Ft, right? And if you take the component of r along the z-axis, my dear student, if you take the component of r along the z-axis, this will, my dear student, please see now. This will become what? Your Fc. This is what? This is the Fc. Now, if you again take a component of Ft, now if you again take a component of Ft along x-axis, this is the component of what? Your Ft. This is the component of Ft along x-axis. This is what? Feed force or axial force. If you take the component of Ft along y direction, then this force become what? That is your radial force. Remember, previously we have discussed, remember, or if you are not remember, then please see. Okay, whatever the component which you take, the component of r in xy plane is what? Ft, and that Ft basically it is nothing, it is a thrust force. It is what? A thrust force. It is a thrust force, my dear. That thrust force is acting in orthogonal plane. That Ft is acting along the orthogonal plane. This is a Ft, thrust force, okay, that is a component of r in xy plane. Now if you take the component of r along the axis of rotation, okay, if you take the component of Ft, okay, across the axis of rotation, so this is what? This is your feed force, or sometime we call axial force, okay, and it is your Ft cos Cs, or sometime we call Ft sin lambda. Lambda is what? Approach angle. You know that lambda equal to what? 90 minus Cs. So Cs equal to what? 90 minus lambda. So if you are going to replace the Cs, so it comes sin lambda. Okay, now what is that? This is your radial force. Okay, radial force generally comes in turning operation, and turning is a oblique cutting. Please remember, turning is a oblique cutting. Okay, so it is Ft sin Cs or Ft cos lambda, right? Ft cos lambda. Now, so this is the thing, my dear student, okay, in two-dimensional, and the cutting force which is acting along the z direction is perpendicular to this plane. Now, suppose that if you have provided a feed to the tool, suppose that if you have provided a feed to the tool, that is in mm per revolution. So after one revolution, the tip of the tool will come from here to here. So this is what? Feed in one revolution. This is the depth of cut, okay, and this is what? This is the width. Now what will be the uncut chip thickness? Okay, what will be the uncut chip thickness, and what will be the width of the chip? Because whatever the chip is going to be produced, it will come like this, it will come like this. So we should know the width of the chip, my dear. My dear, you have to remember the width of the chip is, that is what? W. Width of the chip is, okay, that is the width of the chip is d by That is, D is what? D is depth of cut, right? D is what? D is the depth of cut. D is depth of cut. D is depth of cut, right? D is depth of cut. So D divided by sine of lambda, and uncut chip thickness, that is what? T0 in turning. It will be F sine lambda. Please remember this thing. Please remember this thing. It is a very important, right? It is a very important. Please remember this thing, right? Okay. Now, width of chip, D by sine lambda, uncut chip thickness, that is F sine lambda. Okay. Now, let's move further. Now, I'm going to discuss here, now I'm going to discuss power analysis. Okay. Now, I'm going to discuss what? Power analysis. Okay. Now, in power analysis, before power analysis, I am going to repeat one more thing. Okay, repeat one more thing. What is the thing? The thing is that turning is not. The thing is that turning. Okay, turning is not orthogonal cutting, or turning is oblique cutting. Turning is what? Turning is oblique cutting. Turning is oblique cutting. My dear student, turning is oblique cutting. Turning is what? Turning is oblique cutting, right? Turning is not orthogonal cutting. Turning is not a orthogonal cutting. Turning is 3D cutting, right? Turning is 3D cutting. 3D cutting means 3 force comes in a picture, right? 3 force comes in a picture. What was the forces? Fz, Fx, Fy. You have seen in turning how many forces are there? Here this is Fz, the cutting force which is acting in Z direction. Feed force which is acting in X direction, and radial force which is acting in Y direction, right? So 3 force comes in a picture. Turning is a 3D cutting, means 3 force come in a picture. Next point, turning is not a orthogonal, or turning is not a orthogonal. It is a oblique, it is not a orthogonal. In turning, uncut chip thickness is what? F sine lambda. In turning, the width of chip is what? D by sine lambda. Am I clear? Right? In orthogonal cutting, right? In orthogonal cutting, suppose if you are talking about orthogonal cutting, if you are talking about orthogonal cutting, then in orthogonal cutting, my dear, the uncut chip thickness, that is T0 is what? The depth of cut which is given. Okay, width of chip, the width of chip basically width of workpiece, right? Width of workpiece, whatever be the width of workpiece, that become width of chip. So this is an important thing which you have to always remember. Here lambda is what? Lambda is a approach angle. Lambda is what? Lambda will be the approach angle, right? You have to remember this thing. Now let's move to the force and power in metal cutting. My dear, in this force and power in metal cutting, we are going to what? We are going to find out the power, force and power, right? We are going to force and what? Force and power. Now, force and power. So what we have to do? We have to remember all the formula. Okay, before entering this reason, we have to remember all the formula, right? Shear angle formula, velocity triangle formula. Okay, so this is a very important section. Now let's discuss force and power analysis. So basically what happened, my dear, when you are doing a cutting operation, so there will be four forces which comes in a picture. Four forces, that is a shear force, normal force, friction force, and normal to the friction force. Okay, all the four forces defined below cannot be measurable. Why? Because they are acting in a dynamic condition, right? They are acting in a dynamic condition. Let me draw a figure so that you can understand the thing. Suppose that I am doing a machining operation. Okay, suppose that I am doing a machining operation. 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 Now, see, machining operation, right? Now, this is a chip which is produces. This is a chip which is produces. Now, when the chip is moving, in an upward direction, then on the chip a friction force will come. Let me draw here. Let me draw here. Right? This is a chip, my dear. This is a chip. Okay, this is a chip. So on the chip, a friction force comes. A friction force will come, right? This is the friction force. Because of the tool rake surface, a normal force will also come. A normal force will also come. A normal force will also come. Now, in this shear plane, that is what? AB. Okay, because of the tool, you want to break. Okay, because of the tool, you want to break this crystal structure. You want to break this crystal structure. So you applied, basically, you applied the force. Okay, you applied the cutting force, and because of that cutting force, a shear force is acting on the chip, right? Which are going to break down the bond which is connected with the workpiece. But the chip is going to what, or the workpiece is going to what? Oppose this force, right? Oppose this force. So this is what? Shear force. A shear force which will be act from the workpiece side. You applied the shear force on the chip with the help of tool to separate the chip from the workpiece, but the workpiece will apply the same force, okay, to resist this force, right? Now, there will be a force where, you know the principle, when a force comes in a plane, then there will be a normal force. Then there will be what? Then there will be a normal force. Then there will be a normal force. So this is the normal to the shear plane, and this will be what, my dear? This will be a resultant. Okay, this will be what? This will be the resultant. Okay, this will be the resultant. Just a minute. Yes. So this is a normal, and this is what? This is the resultant. Okay, this is the resultant, that is R. Now again, there will be a resultant. This is, let's say R dash, R dash, R dash. My dear, when you consider a chip as a isolate body, when you consider a chip as a isolate body, when you consider a chip as a isolate body, what we have find experimentally, that the chip velocity, that is VC is what? VC is constant. VC is what? VC is constant. Chip velocity is constant. Here the chip velocity is what? Chip velocity is constant. the net force, the chip velocity is constant. It means the net force on the body, the net force basically on the body, it means it is 0, or whatever be the forces are acting, okay, whatever be the forces are acting on the body, the whose algebraic factorial sum is what? 0, and acceleration is what? Basically 0. So my dear, it is only possible when r equal to what? R dash. When r equal to r dash. So with the help of this, we are able to draw what? A merchant circle diagram. Right. Now we know the relation in between that, and with the help of dynamometer, we are going to measure the thrust force and cutting force. Okay. And that is produces okay, this is the actual cutting force, and these are the component of what? Actual cutting force. That is a cutting force which is acting in the direction of cutting velocity. That is a thrust force which is normal from the cutting velocity. Now you are providing these forces in the system. Okay, you are providing the forces in the system. That's why this r equal to what? That r, because that r is produces in the system and you are providing that r in the system. I am assuming that there is no losses. 100% conversion is there. If 100% conversion is there, then the provided force equal to the produces force in the system. So that r equal to r, and that Fc and Ft will be measured with the help of what? With the help of dynamometer. Okay, with the help of dynamometer, my dear friends. So the two orthogonal component, that is Fc and Fz, the two orthogonal, that is the two orthogonal. Please see, this is what? This is the r, okay, and this is Fc, and this is what? This is Fc, and this is what? Ft. The two orthogonal, because they are perpendicular to each other. The two orthogonal component of actual cutting force, r is what? The actual cutting force. R is actual cutting force. Right? Actual cutting force. R is what? The actual cutting force. So the two orthogonal component, horizontal and vertical, that is Fc and Ft, of the resultant force R can be measured by using dynamometer. Once you know the value of Fc, Ft from dynamometer, and you know the relation in between R, that is the input, and there is a 100% conversion, so you know, you should know the value of that R and R dash. Now you know the interconnection in between the other forces, my dear. Now you are able to draw the merchant circle diagram. Okay, merchant circle diagram. So we are measuring that Fc and Ft with the help of dynamometer, and because of that relation, now we are connect all the forces with that R. So with the help of merchant circle, okay, with the help of this, we are going to draw a merchant circle diagram, right? A merchant circle diagram, my dear. See, this is the tool, right? This is the tool. This is the tool. Okay. Now, this is the actual cutting force, R. If you take the component of R, that is what? Fc, right? Fc. And this is what? This is Ft, right? They are mutually perpendicular. So this is what? This is Fc and this is Ft, right? Now, if you consider all the forces, because here you apply the force on the workpiece, so I am drawing all the, so here this is a force on the workpiece, this is a force which you applied on the chip, right? that is a shear force. That is a shear force. It makes an angle phi from the horizontal surface, and a normal force will comes in a picture. This is a normal force, my dear. This is the normal force, that is Fn, right? So they are mutually perpendicular to each other, and the another force, that is what? A friction force which act on the tool, which act on the chip, that is your friction, and a normal to the friction, that is n. Okay, and this is the alpha, so it is alpha, right? It is mutually perpendicular to each other. This is the beta, that is what? That is a friction angle. So alpha beta, it is 90 minus beta, and it is what, my dear? It is, let's say, x. Now can we get the value of x? Yes, we can get the value of x, because we know that x plus 90 minus beta plus alpha equal to what? 90 degree. So 90 cancel, so x will be come out beta minus alpha. So x is what? Beta minus alpha, my dear, because with the help of dynamometer, again I am going to repeat, because with the help of dynamometer you are able to find Fc and Ft. If you know the value of Fc and Ft, basically Fc is acting in the direction of cutting velocity. If you know the Fc and Ft, you will get the resultant value, that is R, and it is what? Fc square plus Ft square. Once you know the R, you can get any value, any value of the force, which are acting in dynamic condition, and what are they? They are Fs, Fn, and friction, and normal to the friction. Now what are the values? It is very simple. See the value of Fs, that is R, cos, right? X is what? Beta minus alpha plus phi, right? Now Fs, now Fn is what? R, sine, right? Beta minus alpha plus phi, right? Now what is the value of what? Fs, friction equal to R, okay, cos 90 minus beta, right? What is the value of normal? That is R, sine 90 minus what? Beta, okay, 90 minus beta. And what are the even you can correlate the friction and thrust force also. These forces initially, we are unable to find because they are acting in the dynamic condition. Once you get the value of Fc and Ft from dynamometer, you will get the value of R. Once you get the value of R, and once you know the value of angle, then you can able to find all the forces which are acting in dynamic condition. I hope my point is crystal clear. So this is a merchant circle diagram, my dear. MCD, merchant circle diagram. Merchant circle diagram is only valid in orthogonal plane, orthogonal plane or orthogonal cutting, only valid in orthogonal plane and orthogonal cutting, right? So I hope my point is crystal clear to you people. Now let's move to the next point. Let's move to the next point, my dear. Sometime what happened? Beta is what? Beta basically a friction angle. Beta basically a friction angle, right? Friction angle. So you know tan of beta equal to what? That is F by N, okay, from mathematical terms of view, but practically you can find that tan beta, basically F by N is what? Mu. But here coefficient of friction are going to vary. So generally we take average coefficient of friction. Why? coefficient of friction vary in between the chip and tool face? Because when the chip is moving in upward direction, the contact between chip and tool face loses. The temperature distribution is vary. That's why coefficient of friction is not constant. That's why instead of mu, we take what? We take mu average to find out the value of what? Beta. Right? To find out the value of beta. Suppose that in any case, if you are not able to find the value of beta, because for this you need the value of beta, alpha and phi, but if you are not able to find the value of beta, in that case you can directly apply this formula to find the friction force, normal to the shear force, and this is a shear force. What is the friction? Fc sin alpha plus Ft cos alpha. Here you know the value of what? You know the value of Fc, Ft, okay, alpha and phi. If you know these four values, then you can find the friction, normal, Fn and Fs. Okay, it was derived from the Merchant circle, right? From the Merchant circle, but you have to remember directly to save your time in the exam. So friction force Fc sin alpha plus Ft cos alpha, normal equal to Fc cos alpha minus Ft sin alpha, Fn equal to Fc sin phi plus Ft cos phi, Fs equal to Fc cos phi minus Ft sin phi. Now there is a trick to remember this formula. And what was the trick? Let me tell you the trick. Okay, make a row matrix, that is friction and normal. Okay, row matrix of friction and normal. And instead see friction and normal. Now start from sin alpha, write the opposite angle, that is a cos alpha, differentiate the above row, that is a cos alpha minus sin alpha. Okay, now multiply a column matrix of what? Fc and Ft. My dear, you will get the value of friction when you multiply this row into this column. You will get the value of normal when you multiply this row into this column. Now you ended here from n, start again from normal, which is normal to the shear plane. Now this is Fn and this is what? Shear force. Now again start from sine, but instead of alpha write down phi. Okay, write down the opposite angle of sin phi, that is cos phi. Differentiate the above one, that is cos phi minus sin phi, right? Now multiply the column matrix of what? Fc into Ft, right? Now if you want to know the Fn, then multiply this row into this column. If you want to know Fs, then multiply this row into this column, right? So this is a short trick. It's up to you whether you can remember the formula directly or whether you can remember the formula by this trick. Now this is a very good question. By this question you can understand all the concept. See please, the following data from the orthogonal cutting test is available. Here rake angle is given, that is alpha is given 10 degree. Chip thickness ratio is given, that is 0.35. Please, it is recommended that you should note down this data, right? You should note down this data to solve this question. Okay, it will be beneficial to you. Okay, here alpha is what? Here alpha is 10 degree, write down. It is a orthogonal cutting. It is mentioned that it is a orthogonal cutting test. Chip thickness ratio, that is what? R is given 0.35, right? Uncut chip thickness, that is what? T0 is given 0.3, uncut chip thickness is 0.51 mm, right? Width of cut, that is W is 3 mm, right? Yield shear strength of the workpiece, that is tau naught, that is 285 Newton per mm square. It is given to us. Mean friction, again see mean friction coefficient on the tool face is 0.65. My dear, here he says mu average is what? 0.65. Why he says that it is a 0.65? Because I told you, my dear, in basically what happened? Suppose that this is a tool. When the chip is moving in a upward direction, when the chip is moving in a upward direction, then the contact in between the chip and the tool is vary. Then the contact in between the chip and tool is vary, my dear, right? Vary. Contact is going to be what? Vary. This is vary. This is vary. Vary, vary, vary. So mu is not constant. So here coefficient of friction, okay, is not constant. Is not constant. Not constant. It is changing. It is not uniform. It is changing. Friction and normal are not constant. It is changing. So instead of mu, we are going to take mu average, right? Mu average. That is a mean coefficient of friction. Mean coefficient of friction. Now, once you know the value of what? Once you know the value of mu average, okay, you have to find the cutting force, radial force, normal force, and shear force. Now, from this, I think I can easily find out the shear force. But for that, I need the shear angle. I need the shear angle. Okay. I need the shear angle. Okay. Let's move to the solution. Now see, please. See. Solution. Solution. Please see. First of all, if you want to find out the shear force, in orthogonal cutting, shear force, that is what? Tau naught into AS and tau naught. AS is what? W into, that is a width of chip, T naught by sin phi, remember? So you know the value of W, you know the value of T naught, you know the value of tau naught, you need to find out the value of sin phi. So my dear, there phi equal to what? Tan inverse R cos alpha 1 minus R sin alpha, right? So what will be the value of phi? Now, you know the value of R. Here R is what? R is given 0.35. R is given, that is 0.35. So, tan inverse 0.35 cos of alpha. Alpha is what? Alpha is 10 degree. Alpha is 10 degree divided by 1 minus 0.35 sine of what? Sine of 10 degree, right? Sine of 10 degree. So what will be the value of phi? So, okay, 0.35 into cos 10 degree divided by 1 minus 0.35 into sine 10 degree. So here phi will become 20.152 degree. Now, you know the value of phi, my dear. Can we find out the value of Fs? Fs is what? Tau naught, that is 285, I think. 285 Newton per mm square, right? 285 Newton per mm square, right? 285 Newton per mm square. W, that is width, I think 3. And what is the value of W is what? W is, I think, 3. And the uncut thickness, that is T naught. That is T naught. T naught is what? 0.51. 0.51. 0.51, right? 0.51. So W, that is 3 into 0.51. Both are in mm. So mm square divided by sine of what? Phi. 20.152, right? So it will be mm square. So mm square cancel. So you will get the value of shear force. So shear force is what? 3 into 0.51 divided by sine of phi, answer into 285. It will become 1265.67 Newton. Right? So now we know the fourth, I think it's the fourth one. Yes, fourth answer. This is what? This is the fourth one. Let me see. This is the fourth one, right? This is the fourth one. This is the fourth one. Now, once you know the value of shear force, can you find the cutting force? Normal force on the tool? Yes, I can find the cutting force also. But for that I need what? I need the resultant force, right? I need the resultant force. I know that Fs is what? Fs is R cos phi plus beta minus alpha. Fs is R cos. Once you know the value of R, then you can find the Fc, that is R cos beta minus alpha. But for that you need the value of beta. Can we find the value of beta? Yes, I can find the value of beta also. My dear, 10 beta equal to mu average, right? So beta equal to 10 inverse mu average, right? So equal to 10 inverse mu average, that is 0.65. Now you have the value of beta, that is shift 10 inverse 0.65. So it comes 33.02 degree. Now you have the value of beta, my dear. Now Fs is what? 1265.67. R cos phi. Phi is what? 20.152 plus beta, that is 33.02 minus alpha. Alpha is what? I think alpha is 10 degree. Yes, alpha is 10 degree. So now we have the value of R. So okay, cos 20.152 plus answer minus 10, 1265.67 divide by answer. My dear, here see, R is 1735.561 Newton. Now, what is Fc from merchant circle? R cos beta minus alpha. So R is what? 1735.56 cos of beta. Beta, that is what? 33.02 minus alpha, that is 10. So you will get the value of what? Fc. So what is the Fc? Answer into cos of 33.02 minus 10. So 1597.355. This is Fc. And now Ft, that is R sin beta minus alpha. Beta minus alpha. So 1735.56 sine of 33.02 minus 10, right? So 1735.56 into sine 33.02 minus 10, it comes about 678.69 Newton, right? So you know the value of Fc, you know the value of Ft. Cutting force, okay, you need the, you should know the value of what? Normal force. Normal force, my dear. What is a normal force? Normal force are what? Friction is R cos 90 minus beta, R sin 90 minus beta. So R cos beta. So normal is what? R, that is 1735.56 cos of beta, that is 33.02, right? 02. So just see what is the value. 1735.56 into cos 33.02. It comes, normal comes 1455.23 Newton. Now, if you talk about the radial force, here radial force is 0. Why radial force is 0? Because radial force comes in a turning. Radial force comes in a turning, and it is a purely orthogonal cutting, not a turning. I told you that the radial force, see, I told you in the turning analysis, told you in the turning analysis that radial force, Fr is what? Fr is the radial force, okay, radial force, and that radial force will come into the turning, not in orthogonal or not in orthogonal cutting. So here the radial force is what? Here the radial force is 0. Here the radial force is what? Here the radial force is 0. So I hope you understand the concept behind this. Now, okay, let's move to the next slide, my dear. That is a merchant analysis. What merchant analysis will say? Merchant analysis will say that is a minimum energy, okay, that is a 100% conversion, or minimum energy or minimum energy, okay, required, minimum energy analysis. It is based on what? 100% conversion, okay, or minimum energy analysis, or what? Or the minimum energy analysis. You can get the value of what? You can get the value of phi. That is a merchant analysis. That is pi by 4 plus alpha by 2 minus beta by 2. My dear, the above merchant shear angle is theoretically proven shear angle relation because of some of the assumption taken during the analysis, like energy required for producing thrust force is negligible. Here the required energy, okay, we consider that is what? That is the negligible. Also by varying the shear angle, basically what we have assumed, we have ensured that stresses include, we have ensured that to ensure that stresses include is equal to ultimate shear stresses. Ultimate shear stresses, it is required to determine the optimum shear stress. So this is a optimum shear. This is what? This is a optimum shear angle. This is a optimum shear, okay, angle, which is based upon the minimum energy analysis or 100% conversion. Okay, the minimum energy, that is whatever be the strength of material, we consider that this is the minimum energy which is required. We consider that this is a minimum energy which is required to deform the crystal, or there is a minimum stress which is required to deform the crystal. We assume that there is a 100% conversion, there will be no loss. There will be no loss. I hope you understand this thing. Also, there are some fact, my dear. There are some fact which you should know. Okay. There is a term which comes, which is known as machining constant. Machining constant. Okay. Machining constant. A term which comes, that is a machining constant, Cm. Right? Cm. Now that Cm, in that case, that Cm equal to what? That Cm machining constant is, 2 phi plus beta, okay, 2 phi plus beta minus alpha, that is equal to what? 90 degree. Please remember machining constant for this for this analysis, right? Now AC, a cross-sectional area during cutting. Suppose that much cross-sectional area I am going to cut, okay, with the help of what? With the help of tool. This is my tool and I am going to cut that much cross-sectional area. Suppose that this is what? This is uncut chip thickness T0. This is the width of the chip, or width of that workpiece. So the cross-sectional area which I am going to cut is what? W into T0, right? W into what? Into T0, right? W into T0. That's the cross-sectional area which you are going to cut, or the power or the energy which you are going to apply, right? Which you are going to apply, that Fc and Ft, or that the resultant or actual cutting force which you are applying, okay, on that area. that cross-sectional area which you are going to cut. So I hope you are now understand the meaning of cross-sectional area, right, my dear student? Actually, there are some other analysis also, like Lee and Schaefer analysis. Okay, apart from merchant analysis, there are some other analysis like Lee and Schaefer analysis. Okay, Lee and Schaefer analysis. Lee and Schaefer analysis. According to Lee and Schaefer analysis assumption, the value of the relation in between phi, friction angle, and alpha is what? That is phi plus beta minus alpha equal to what, my dear? 45 degree. But generally in the exam you have to apply merchant analysis until unless he mentioned that you have to apply Lee and Schaefer analysis or any other analysis, right? Or any other analysis. Suppose that there is a Stabler analysis, there is a Stabler analysis, right? In Stabler analysis, what you have to write down? There is a relation in between phi, beta and alpha. That is what? Phi plus beta minus alpha by 2 equal to 45 degree, right? But you don't have to apply, okay, until or unless examiner mention. Okay, in general you have to apply merchant analysis. In journal you have to apply merchant analysis. Clear? Now, actually I was talking about the material removal rate. In material removal rate, that cross-sectional area play a very important role. If you want to find out material removal rate, then what will be the material removal rate? If you know the cross-sectional area during cutting operation and if you know the cutting velocity. V is what? V is the cutting velocity. Okay, cutting velocity. If you know the cutting velocity, then what will be the MRR? My dear student, material removal rate, that's a material removal rate is what? Cross-sectional area into cutting velocity, right? Cross-sectional area into cutting velocity. You know what is the cross-sectional area? Suppose that if you are talking about, actually, let me explain you. Suppose that in orthogonal cutting, right? In orthogonal cutting, the MRR is cross-sectional area which you are going to cut into cutting velocity. Now, the cross-sectional area which you are going to cut is what? Width into uncut thickness into cutting velocity. But if you are talking about turning, that is what? Oblique cutting. Turning, that is what? Oblique cutting, right? Turning, that is what? Oblique cutting. So in oblique cutting, how can you find the MRR? In turning, you can find the MRR in a similar method, that is cross-sectional area, cutting cross-sectional area into velocity, and that AC equal to W into T0, okay, into V. Okay, but in turning, what is W? W is d by sine lambda, and T0 is F into sine lambda into V. So sine lambda cancel, it comes F dV, right? It comes F dV mm cube per unit time. It is mm cube per unit time, right? So this is a very important thing which you have to remember, right? Which you have to remember. I hope you understand the thing. Okay, okay, yes. So now we are going to discuss a specific cutting energy, right? A specific cutting energy. My dear, what is a specific cutting energy? A specific cutting energy is nothing but the energy required for removing unit volume of material from the workpiece. That is work done divided by material removal rate, right? The work done divided by material removal rate. So basically, energy required for removing the unit volume of material from the workpiece is called specific cutting energy. So basically, the power which is going to be consumed is what? That is cutting force into cutting velocity. That is a power which is going to be consumed. And how much material removal rate? The material removal rate which is going to be removed is what? That is mm cube, right? Mm cube per second. So that is what let me write in the very simplest form, in a very simple form. So cutting velocity, right? So what is the specific cutting power? It is a power divided by MRR, and power is nothing, that is your cutting force into cutting velocity divided by material removal rate. Material removal rate, that is a cross sectional area which is going to cut into what? Cutting velocity. Okay, cross sectional area into cutting velocity. Now please remember one thing. What is that? Here the force is in Newton, and here the cutting velocity in meter per second. Okay, now here cross sectional area which you are going to cut, initial cross section area which you are going to cut, A0 or AC, let's say it is AC, right? Let's say it is what? It is okay. Okay, I will write it again. What I'm saying basically, see, okay, I will write it again. See, just forget this thing. Just forget this thing. What is the specific cutting energy? That is the power divided by material removal rate. Power is what? Power, that is your cutting force into cutting velocity divided by cross sectional area which you are going to cut into cutting velocity. Now generally what students do? Generally students are going to cut that V cutting velocity. My dear, unit wise that we are different, so please don't cut directly. Why? Because here MRR is in mm³ per second, right? And power is what? Joule per second, right? Joule per second. And power is what? Joule per second, that is Newton meter per second. So basically if I'm come here, so that FC is in Newton into that cutting velocity is in meter per second, right? Meter per second divided by AC, that AC in mm² into VC, that VC in per second, right? So don't cut that cutting velocity directly. After converting you can cut, right? Now if you cut unit wise, second cancel, Newton meter is what? Joule, Joule per second. So okay, so this will become specific as a, if you are talking about what? Specific cutting energy, right? Now let's start the tool wear, tool life and machinability. My dear, if you talk about the tool, right? If you talk about the tool, so there are two types of wear. Generally two types of wear comes in a picture. First wear is what? The first wear. Now let's start with tool wear, tool life and machinability, right? Now see here, if you are talking about tool life, okay, and or tool wear, my dear, there will be two type of wear, slow death, and basically there are two type of death, that is a slow death and sudden death, right? Let me draw the figure. See, this is a tool, this is a tool, right? As you can see, so this is a rake surface, okay. In slow death there will be a basically what? Slow death, basically the gradual or progressive wearing away of rake face in terms of what? Crater wear. So on the rake face a crater will be produces. Okay, a crater will be produces, or a flank wear. This is what a crater wear on the rake face. This is the rake face, my dear. On the rake face, a crater wear comes in a picture. A crater wear comes in a picture. A crater wear comes in a picture, right? Or on a flank. On a flank, this is a flank wear. It's a little bit a type of scratches. A type of scratches will become. A type of scratches will become. Okay, so this is what a flank wear. Majorly, it will occur on a side flank, but little bit on the below the nose and little bit on the end flank. So this is what? This is a flank wear. Flank wear, right? Flank wear. Okay, which happen just below the cutting edge. Okay, on the flank. Now, this comes in the category of what? Slow death, because we know the reason of the wear. Basically, flank wear will happen because of low cutting speed. Low cutting speed. Low cutting speed, right? And the crater wear will occur at high cutting speed. At high cutting speed. My dear, if you know the reason of the wear, if you know the reason of the wear, if you know the reason, then you can, okay, treat that reason, okay, so that the wear is going to be what? Minimizes. So that wear is going to be what? Minimizes. Now, so it comes in a slow death. Now, what is a sudden death? Basically, failure leading to premature end of the tool, right? The sudden death type of tool failure is difficult to predict, right? Is difficult to what? Predict. Tool failure mechanism include plastic deformation, right? Plastic deformation, brittle fracture, fatigue fracture, or you can say, or edging of the, edging of the cutting edge, right? It is difficult to predict because there are many reasons for that wear. Okay, that's why it comes under the sudden death. That's why it comes under the sudden death, right? So, in short, you have to remember this. Okay, in short, you have to remember this point. Okay, in short, you have to remember this point that a flank wear and crater wear. Flank wear occur due to low cutting velocity, and crater wear occur due to high cutting velocity. Now, that's why you know the wear, that's why it comes under slow death. Okay, now the third type of wear, that is chipping of the cutting edge. Chipping of the cutting edge. My dear, we are not able to find the exact reason of the wear. That's why it comes in sudden death category. Right? So let's talk about the flank wear because it is very important. Okay, flank wear is very important, right? Very important. Why it is very important? It is very important because flank wear, okay, flank wear affect the surface finish of workpiece, right? So we don't want, okay, we don't want a bad surface finish. So that's why we have to minimize that flank wear, right? For that purpose, we are going to study the nature of the flank wear. The nature of the flank wear, here you can see in the figure, my dear student, on the y-axis there is a wear, on the x-axis there is a time, right? So you can see the wear initially start from t equal to 0, and at a particular, up to a particular time, okay, it form a curve. It form a curve at up to a particular time, it form a curve. See, so from here to here, the wear initially, the wear is what, my dear? The wear is what? Initially, the wear is high, but as the time passes, the wear goes decreases. Okay, the wear goes decreases. The wear goes decreases. The wear goes decreases. Okay, the wear goes decreases. Okay, now at this point of time, please see, at this point of time, the rate of wear, that is wear versus time, is constant, my dear. The rate of wear is what? Is constant up to a certain point of time. Up to a certain point of time. Up to a certain point of time, right? Up to a certain point of time. The rate of wear, that is a wear rate, is constant. The wear versus time slope is what? Is constant. After some point of time, again the wear rate gradually, gradually increases. Again the wear rate gradually increases. Here you can see that wear rate gradually increases, right? Increases. Wear rate gradually increases, right? Wear rate is what? Wear rate is gradually increases. Clear? Now, actually what happened, this graph is very important. On the basis of this graph, lot of question was asked. Actually, this graph is obtained experimentally. Behind that graph, there are a lot of reasons. One of the reason is that of the flank wear is that abrasion by hard particle and inclusion in the workpiece. Second, shearing of the micro welt, okay, between the tool and work material. What is the shearing of the micro welt? Shearing of the micro welt, that is a built up edge. Built up edge is going to be what? Broken out, okay, after some point of time, and because of that, what happened? Some scratches will be formed. Abrasion by fragments of built up edge, already I told you about the built up edge. Abrasion of fragments of built up edge, plugging against the clearance face of the tool, that is a flank face or end flank, right? At low cutting velocity, there is a more tendency of formation of what? More tendency of formation of built up edge. And if the built up edge form, then built up edge regularly sheared off, and it will do a plugging on the flank surface, okay, whether it is a side flank or a end flank, right? And generally side flank comes in a contact with the workpiece. So that side flank basically spoil, okay, spoil the surface finish of the workpiece, right? Also, if you increase the material removal rate, okay, instead at low velocity, you can increase the material removal rate. How you can increase the material removal rate? How you can increase the material removal rate? By keeping the low velocity. Material removal rate in turning is FdV. Suppose V is low, but if I increase F and if I increase depth of cut, then what happen? By increasing feed and depth of cut, what happen? Lot of heat is going to be produces, and because of lot of heat, built up edge formation will occur. And because of built up edge, you know what happened? When the built up edge is going to be broken off, sheared off, it will do a plugging action on the clearance face of the tool, right? Clearance face of the tool. So I hope this point is crystal clear, my dear. Now effect of the, I already told you the effect of the flank wear. Effect of the flank wear is what? It directly affect the dimension of the component. Okay, so flank wear is usually the most common determination of what? Determination of tool life, right? So this is what basically, this is the primary wear zone. In primary wear zone, basically what happened in primary wear zone, basically the reason where the sharp cutting edge is quickly broken down and finite wear length is what? Stabilized. In secondary wear zone, this is what? This is the secondary wear zone where wear rate is constant. Okay, the reason where the wear progresses at a uniform rate, right? Now this is a tertiary wear zone, my dear. This is what? This is a tertiary wear zone. In tertiary wear zone, the reason where the wear progresses at gradually increasing rate, the reason where wear progresses at gradually increasing rate, right? In tertiary region, the wear of the cutting tool has become sensitive to increase tool temperature due to high wear length, right? So before entering into the tertiary region, it is highly recommended to grind to regrind the tool or to change the tool, right? To change the tool. So I hope the point is crystal clear. Now let's move to the next slide. That is a question, my dear. Here on the y-axis, you can see on the y-axis a wear height that is in mm is given. Okay, that is 0.8, and on x-axis there is a time in minute, right? And what it says, it is a curve, and from that point up to that point there is a straight line. So at 10 minutes the wear height is 0.8 mm, right? And at 60 minutes the wear height is 2.0 mm, right? During machining, the wear length h has been plotted against the machining time t as given in the following figure. For a critical wear length of 1.8 mm, the cutting tool life, I mean, suppose that here, right? Suppose that here, okay, suppose that here 1.8 mm. At what time that critical okay, that critical wear length, okay, is obtained? You have to find this thing. So the question is pretty simple. Okay, the question is pretty simple. Suppose that, so you have to find what? You have to find the equation of line, because this portion will lie where? First of all, see, this portion will lie here, where the wear is what? Constant. So find out the equation. Okay, straight line equation. A straight line equation. Find out the straight line equation, right? Suppose that this is the point 1, that is 10, 0.8. Okay, point 1, that is what? X1 and Y1. This is what? Another point of the line, and it is what? 60, 2, right? That is what? X2, Y2. Now find out the equation of line. You know that, okay, y minus y1, sorry, y minus y2, yes, y minus y1 divided by x minus x1 equal to y2 minus y1 divided by x2 minus x1. So y is what, my dear? Here y, in general, y is what? 1.8. This is what? X comma y, right? X comma y. So y, here y is 1.8, and this is what? T, right? So write down here or you can solve on the other slide, on the other page. I will try to solve here. Okay, I will try to solve here. See here. Now, y that is what? 1.8 minus sorry, yes, y1 that is what? 0.8, right? Divide by x, that is what? T, you have to find, minus x1, that is what? 10, equal to y2, that is what? 2, minus y1, that is 0.8. Okay, divide by x2, divide by what? X2, right? X2, that is 60, minus 10. Now solve for t. Now solve the equation for t. Now solve the equation for t, right? Solve the equation for t. Once you solve the equation for t, you will get your answer, right? You will get your answer. What is that? Let me solve. 2 minus 0.8, answer, divided by 60 minus 10, answer. Okay, answer, or 1.8 minus 0.8 divide by answer, and plus 10, answer plus 10, 51.66. So t comes 51.66 minute. So the right answer is option B. The right answer is option B, my dear student, right? The right answer is option B. Now let's discuss about the Taylor's two-life equation. My dear, the Taylor's two-life equation generally based on the flying fear. Okay, not totally on the flying fear. Other parameter also, like cutting velocity, cutting condition. Cutting condition means type of the lubricant which you are providing. Okay, which you are providing, type of the tool, type of the workpiece. On the lot of basis, lot of other parameter. Okay, tool life equation is based on lot of other machining parameter. So overall, the tool life equation will become V t to the power n equal to C. V is what? Cutting speed, that should be in a meter per minute. Tool life should be in minute. Okay, should be in minute, and n is the exponent, depend on the tool material. C is what? A constant which is based on the tool, work material. Okay, and the tool material, right? And the cutting condition also, Now there is a question. Okay, there is a question. In orthogonal machining operation, the tool life is obtained 10 minute. Okay, t1 is given, that is what? 10 minute at a cutting speed of what? At a cutting speed of 100 meter per minute, right? 100 meter per minute, while at 75 meter, that is V2, while at 75 meter per minute, right? Per minute, cutting speed, the tool life, that is T2, is what? 30 T2 is what? 30 minute. Okay, 30 minute. The value of the index in the Taylor's tool life equation is, my dear, here the tool is same. Here, what is the thing? Here the tool is same. Here the workpiece, material of workpiece is same. Condition is same, right? Condition is same. I'm only changing here. Here only we are changing velocity and t. So in both the case, constant C, cutting constant is what? Same. So you can directly apply V1 T1 to the power n, V2 T2 to the power n, right? V1 T1 to the power n equal to V2 T2 to the power n. Now solve here. So what is a V1? V1 is what? That is 100 into T1, that is what? That is 10 to the power n. Okay, and V2 is what? 75 into T2 is what? 30 to the power n. Now solve this equation for the value of what? For the value of n. Once you solve the value of n, then you will get the value, okay, exact value of n. Now I'm going to solve this equation. Yes. So the value of n will be 0.262. This is the value of n, right? Now, extended or modified Taylor equation. One more thing I will tell you in the previous equation. One more thing I will tell you from the previous equation, that the tool life equal to C by V 1 by n. Here, according to the tool life equation, the tool life is based on cutting condition. Cutting condition means constant based on tool and work material, and cutting condition means type of lubricant which you are using. Cutting velocity on the tool, exponent which is based on the tool. Okay, but here in the extended or modified Taylor equation, extended or modified Taylor equation, the tool life is not based on only on one parameter. It is here in extended or modified Taylor equation, the tool life will be based on feed and depth of cut. So the equation is what? Velocity into t to the power a, or sorry, t to the power n, feed to the power a, depth of cut to the power b equal to constant. Here v is as usual is same, where okay, v is a cutting velocity, it should be in meter per minute, right? T is tool life in minute, right? F is feed, okay, that should be in mm per pass. D is depth of cut, it should be in mm, right? Here NAB are what? Are the constant, right? NAB are the constant and C is the constant, right? So my dear, here you can see the tool life is what? The tool life C to the power 1 by n divided by velocity to the power 1 by n, feed to the power a by n, depth of cut to the power b by n. Okay, depth of cut to the power b by n. So here tool life will depend on velocity, feed and depth of cut. Experimentally, it was found that 1 by n is greater than a by n, and a by n is greater than what? A by n is greater than b by n, right? Now, this is a power of what? This is a power of what? Velocity, feed and depth of cut. It means the power of velocity is more. It means there will be more change in velocity. If there is a more change in velocity, then there will be a more change in tool life. Now, a by n is a power of feed. It means power is less. If you change the feed by same amount, then there will be less change in feed. If there is less change in feed, then there is a less change in tool life compared to what? Compared to cutting velocity. Similarly, b by n is a power of depth of cut, and b by n is less than a by n. Means if you change depth of cut by same amount, then there will be a very less change in depth of cut. If there is very less change in depth of cut, then it will affect the tool life very less. It means hence velocity affect the tool life more, okay, followed by feed and depth of cut. Please remember, important point, okay, this is an important point. What is that? The important point, cutting speed has the greater effect, greater effect, okay, cutting speed has the greater effect, followed by feed, and depth of cut, okay, and depth of cut respectively, okay, respectively. Now this is an important thing. Now to prove that, I'm going to solve one numerical, which is a very interesting and very important numerical. Now see this. Here this question was asked in ESC 1999, okay, and it is a very, very important question. Let's see this question, right? Let's see this question. What the question is saying? The question is saying that the following equation for the tool life was obtained, okay, for HSS tool A. A 60-minute tool life was obtained, okay, a 60-minute tool life was obtained. A 60-minute tool life was obtained. T0, 60-minute tool life was obtained, right? Using the following cutting condition. And what is the cutting condition? V T to the power, please write down 0.13, feed to the power 0.6, right? Depth of cut to the power 0.3 equal to C, where initial velocity is given, that is V0 equal to 40 meter per minute, right? 40 meter per minute. Here F0 is 0.25 mm, right? And depth of cut, that is D0, initial depth of cut is given, that is what? 2.00 mm, okay. Calculate the effect on the tool life is speed, feed and depth of cut are together increased by 25%. Suppose that if we are increasing V0, F0, D0, okay, 25% increase if velocity, feed and depth of cut are increased by 25% together. Then velocity, then here please write down velocity equal to what? 40, 1 plus 0.25, okay, and feed, that will be what? Feed is 0.25 into 1 plus 0.25 depth of cut, that is 2, 1 plus 0.25, right? Now 40 into 1.25, so 50, it will be 50 meter per minute, right? Now 0.25 into 1.25, it will be 0.3125 mm, right? And depth of cut 2 into 1.25, that is 2.5, here 2.5 mm, right? So what will be the tool life? For that we need to find the value of C. Now V0 T0 to the power 0.13 into F0 to the power 0.6, okay, and also you can write D0 to the power 0.3 equal to what? C. So V0 is what? V0 is 40 into T0 is what? T0 is 60 to the power 0.13 into F0, that is 0.25 to the power 0.6 into D0, that is 2 to the power 0.3. It is coming, C is coming what? 36.499, right? 36.499, that is the value of C. Now suppose that because in the first case velocity, feed and depth of cut are increasing together by 25%. Then the tool life is C to the power 1 by n, right? V to the power 1 by n feed. What is n here? What is n here? The value of n is what? 0.13. 0.13. 0.13 divided by velocity to the power 0.13. V to t, okay, 0.13, right? 0.13, 1 by 0.13 feed. That is what? That is 0.6 divided by 0.13. 0.6 divided by 0.13. Depth of cut 0.3 divided by 0.13. Okay, 0.13. Now, what will be the tool life, my dear student? Here just put the value C. Here just put the value, right? Here just put the value. So T equal to C, that is 34.99 to the power 1 divided by 0.13, right? Velocity is what? 50 to the power 1 divided by 0.13 feed. That is what? 0. I think 0.3125. 0.3125. 0.3125 to the power 0.6 divided by 0.13. Depth of cut, that is what? 2.5 to the power 0.6 divided by, not a 0.6, it is a 0.3. It is a 0.3 divided by 0.13. Am I right? Let me check. Depth of cut, that is 2.5, and it is 0.3 divided by 0.13. Now calculate the tool life here. Calculate the tool life here. Okay, if you calculate the tool life here, you will get 2.29 minute. 2.29 minute, right? You will get 2.29 minute. Now B, suppose that individually if you are increasing, if velocity increased by 25%, then if velocity is increased by 25%, okay, then velocity is increased by 25%, it means 50 t to the power n, that is n is what? 0.13. okay, feed is as usual is same, that is 0.25 to the power 0. I think it is a 6, and depth of cut is what? 2, that is 0.3 equal to C. C is what? Again 34.499, right? 34.499. If you are going to increase what? If you are going to increase the velocity by 25%, so 50 t to the power 0.13, please check, 0.25 to the power 0.6, and depth of cut, that is 2 to the power 0.3 equal to 34.99. If you are going to calculate, then T will become, my dear, 10.79, okay, minute, right? 79 minute. This is a part 1. Okay, now my dear, if you are going to increase feed by 25%, it means velocity remains same, that is 40 t to the power 0.13, feed is 0.3125 to the power 0.6, depth of cut is 2 to the power 0.3 equal to what? 34.499. Now what will be the value of T here? If you are going to increase the feed, right, if you are going to increase the feed, then what is going to be happen, right? Please check. 40 into t to the power 0.13, 0.3125 to the power 0.6, and 2 to the power 0.3, 34. It is a 34 and 30. Oh, sorry. It is a 36. It is a 36. Sorry, by mistake. Okay, it is a 36, not a 34. Not a 34. Actually, in my calculator, I have feed it 36.499. Right here, I also have written 36.499. Okay. So please make changes. 36.499, it is a 36.499. Now if you are going to calculate the value of t, it will become 21.4 minute, right? Now third, depth of cut is increased by 25% only. Then velocity will same, t to the power 0.13, feet 0.25 to the power 0.6, 2.5 to the power 0.3, 36.499, right? 36.499. Now calculate the value of t. Here you will get the 35.5 minute. My dear, you can see by increasing the depth of cut, tool life is 35.5, decreases from 60 to, it will decreases to 35.5. If you increase the feed by same amount 25%, then from 60 minute to tool life decreases to 21.4. If you increase the velocity by same amount, then tool life is going to decreases from 60 to 10.79, which is very large. So velocity affects more. It is proved that velocity affects more, my dear. Okay, it is proved that velocity affect more. So thank you for watching this video. We are going to meet in the next session.